Good evening everyone. Welcome to Gate Academy Global. So everyone please join the session and just confirm me audio and video both are clear or not. Today just I am going to take a very small session and here I will discuss revision. Actually I will not discuss all the things but exactly the important thing and that will be helpful for your revision purpose, ADC and DAC. Many students are because demanding such please just at least complete this topic. So now I am going to conduct. Okay, now okay, so okay, you are saying sir when start communication? So from tomorrow. Okay, so I am planning today. Okay, so tomorrow you will get maybe tomorrow. Okay, 100% I cannot say, but maybe from tomorrow I will start communication. After that signal and system will continue. Okay, so from tomorrow maybe I will start communication same time at 5 p.m. Okay, so now everyone just share the session. Everyone please share the session. Okay, now okay, and just confirm me audio and video both are clear or not. Please just confirm me. Just confirm me audio and video both are clear or not. Everyone who are watching the video, please confirm me everything is perfect so that we can continue the session. So our today topic is ADC and DAC. Okay, if you will respond more, then definitely I will discuss some more good thing. Okay, now okay, everything is perfect. Okay, now so here in ADC means analog to digital converter, analog to digital converter and digital to analog converter. Okay, so already the same topic we will also use in a communication system for electronics engineering students. Okay, but in digital in different way exactly we have to study. So in digital analog to digital converter and digital to analog converter, in real life first process is analog to digital. Suppose this is my voice, suppose this voice is going to be converted into digital, and by digital this is going to be transmitted over the internet, or you can say through the internet, and then you are receiving by again digital to analog converter. But here first we will study digital to analog converter and then we will study analog to digital converter. So just I am going to discuss here revision according to your gate point of view. Okay, so after this class definitely maybe you can handle any question from this topic. Okay, so first I am going to take digital to analog. First I am going to take digital to analog okay converter. So here what exactly you should know, I hope definitely you have studied this topic. Okay, so just I am going to recall each and every important point here. Suppose we are going to take one digital to analog converter, and here everything will depend on the size. So it can be 3 bit, 4 bit, it can be 5 bit. Okay, so digital to analog, so input bit can be here digital or you can say binary. Okay, here this is n bit and this is input, and one you will get a analog you can say this is a analog output. Okay, now but here two important thing is okay, here two more important thing are also present. One important thing we can say, oh sir, reference voltage. This reference voltage is very important term. Second important term is here FSV, full scale voltage, and third important term is here resolution. Okay, so just I am writing resolution voltage. I am not writing percentage resolution, resolution voltage. So here sir there are some difference between V reference and FSV. This is very important thing. Sir there are some difference between V reference and FSV. So V reference is the maximum applied voltage. Okay, FSV, okay, FSV represent that is a maximum full scale voltage. That is if you will convert, suppose all the bit is 111, and if you will convert that 111 into analog, so that output will be represented by full scale voltage. And what is the resolution voltage? If your input bit only if LSB bit is 1, so you will get a resolution voltage. So by this diagram I want to explain you. Suppose I am considering sir 4 bit DAC. So if this is 4 bit DAC, if this is 4 bit DAC, so here you will apply one reference voltage, and this is 4 bit DAC. Now if suppose all the input bit are 1111, if all the input bits are 1111 and corresponding to this your output voltage, Suppose I am writing this is output voltage. So if all the bits are 1 1 1 1, corresponding voltage is FSV, full scale voltage. Full scale voltage. And one important thing, sir, V reference and FSV, okay, this is not same, both are different. This FSV, V reference is the reference voltage applied to this DAC, 4-bit DAC, and this reference voltage will be divided according to the number of bits. So here, suppose second diagram, if I am going to consider, suppose again 4-bit DAC, 4-bit DAC, and suppose this is MSB, this is and this is LSB. Suppose this is 0 0 0 and this is 1. I can say this bit is LSB bit and this bit is MSB bit. So if LSB bit is 1, then corresponding output voltage you can call, this is nothing but resolution voltage. This is nothing but resolution voltage. Okay, so first thing you should know this thing. And resolution voltage we will represent by delta. You can also represent by this del. So by any way you can represent this. Okay, so this is the resolution voltage. Now if I will ask you one question. Suppose we have one 4-bit DAC, 4-bit DAC. Suppose if MSB bit is 1. Suppose if MSB bit is 1 and remaining bit is 0. So you can say this is MSB, and this is your LSB, So then what will be the output? Here the reference voltage is V reference. This is V reference and this voltage is V reference. Then what will be the output voltage here? So in this case output voltage will be, here how you remember. So first, for this output voltage is del. Okay, now for this output voltage is 2 del. For this output voltage is 4 del. And for this output voltage is 8 del. Like this you should remember. So for this LSB bit, this output voltage is del. Now for this second bit, this is 2 del, and for this you can say this is a 4 del, and for this you can say sir this is 8 del. This is for 4 bits, so you can get one relation. So for this LSB bit, your output voltage is resolution voltage. So for this bit, that will be multiplied by 2. For this bit, multiply by 4. For this bit, multiply by 8. So you can write 2 raised to power. This is a 2 raised to power 0 into del, 2 raised to power 1 into del. This is 2 raised to power 2 del. This is 2 raised to power 3 del. So like this, any number of bits can be provided. So you can see if this is 1, remaining bit is 0. So you can say, sir, this is nothing but 8 del. You can say, sir, this output we are getting here, sir, this output is 8 del. So in this case, you are getting 8 del. So now, for any number of input, for any input, at least you can provide the output voltage. Okay, output voltage in terms of step size. This del is also called step size, and we can also say this is nothing but step size. Okay, so for any input voltage. Now we have to find out one relation between V reference and FSV and the del. So we have to find out one relation between V reference, FSV and step size, or you can say resolution voltage. Okay, so what can be the relation? So what is V reference? So what is V reference? Or you can say, sir, what is step size? So if you remember step size, sir, step size is nothing but this V reference is going to be divided by number of bits, means 2 raised to power n. Like this you can remember, sir, step size is equal to V reference divided by 2 raised to power n. So from here you can also write, sir, what is V reference? This is 2 raised to power n times of del. So V reference is 2 raised to power n times of del. Okay, now similarly, sir, what is FSV? Then full scale voltage. What is full scale voltage? So full scale voltage formula we can write, sir, this is 2 raised to power n minus 1 times of del. So what is the difference between these two? So you remember this difference. So V reference and full scale voltage difference is step size. One more thing you remember, sir, V reference minus of full scale voltage is nothing but a step size. This is a voltage, not a percentage. Okay, so this thing you remember. Second, you remember, sir, what is V reference? V reference is nothing but 2 raised to power n times of del. Next, you remember, sir, full scale voltage is nothing but 2 raised to power n minus 1 times of del. Okay, from here you can also write, sir, what is del? So del you can write, sir, V reference divided by 2 raised to power n, and again del you can write. Similarly, you can here write, sir, this is FSV divided by 2 raised to power n minus 1. Okay, so both the formula are same. So if you are going to use FSV or you are going to use full V reference, but by recommendation, always you have to target FSV. Okay, this is very important. Always you have to target FSV. Now my question, how you can write this? If this is step size, this is 2 del, this is 4 del, this is 8 del. What I can write this 8 del? If MSB is 1. So here if this is 4 bit, so here sir this is V reference by 2 raised to power 4. 2 raised to power 4 means you can write 16 del, or you can write here the V reference is the 2 raised to power 4 into del 16 del. So what will be the 8 del? V reference by 2. So if MSB bit is 1, so this value is nothing but sir V reference by 2. V reference by 2. Clear this thing? This you can also remember. If all the bit is 1, this is FSV voltage. If LSB is 1, this is the resolution voltage or step size. If MSB is 1, you can say, sir, this is V reference by 2. In another way, you can also write in terms of step size. You can also say, sir, this is 2 raised to power 3 del. Or you can say, okay, 2 raised to power, this is 2 raised to power 2 del, 4 del. Okay, but in this way, you can remember this 3 things. At least you should know for MSB1, for LSB1, and for all the bits are 1. Okay, and this relation should be very much clear to you. Now here the second important thing, so what is a percentage resolution? So sometime examiner are interested in percentage resolution. Okay, and in this point many time students are wrong. So I hope this thing is clear to you. What is V reference, what is full scale, and what is resolution voltage. Okay, and I hope everybody remember this thing, and I hope everybody remember this thing. I hope everybody remember this thing. Okay, yeah, good evening Biswa. Okay, now I hope everybody remember this thing. Okay, now come to the point. Okay, I promise you after this 2 hour of maybe 2 hour of classes I will conduct 2 or 3 hours, and after this in GIT 2022 every question you can handle from the ADC and DAC. Okay, so now this thing you should know. Now here okay, this thing you should know. Now sir, what is percentage resolution? So what is percentage resolution? Many times students are wrong here. So percentage resolution, okay, so percentage if you will write, suppose 60%, with respect to whom? This is very important thing. So if you are saying, sir, resolution voltage is 60%, 60% with respect to whom? This is very important thing. So percentage resolution you can write, this is step size, but here this is with respect to whom? With respect to whom? So percentage resolution formula we can write. So this is 1 by 2 raised to power n into 100%. 100% of V reference. So you have to write here of V reference. Of V reference. Okay. In another way, if I want to write, sir, percentage resolution. So second formula we can write for percentage resolution 1 upon 2 raised to power n minus 1 into 100% of full scale voltage. Full scale voltage. Both the answer will be same. If you are assuming 1 upon 2 raised to n minus 1% of full scale voltage. So suppose this answer is 60%. So resolution only you will not get, suppose 5%. So from here again you will get 5%. But this value is different, this value is different, but here reference is also different. So if I will tell you 5% of 100, if I will tell you 5% of 100, that will be 5. But so this, if I will tell you 10% of 50, so again this will be 5. Similarly, this percent of V reference and this percent of FSV, answer will be same. Answer will be same. So this is very important point. Generally, student will write only this and only this. But with respect to whom? Now, if examiner will not provide you, if examiner will not provide you with respect to whom, so you have to think. So in general, we will target FSV. In general, we will target FSV. If examiner will provide 5% is the resolution. So with respect to whom 5%? So if examiner will generally provide, but if they will not provide, so you have to consider with respect to FSV. Okay, this is a controversial part. At least they have to provide. Okay, I hope this thing is clear to you. I hope this thing is clear to all of you. Okay, so now suppose here I am going to take one question for you. So one problem for you, and this is very simple problem. Suppose for example, if we have 4-bit DAC. So suppose if we have 4-bit DAC, and for this 4-bit DAC, suppose for example for 0101, for this 0101, Suppose this voltage I am considering, suppose this is 1.25 volt. Suppose this 0101 corresponding voltage is given, okay, for 4-bit DAC. Now if examiner will ask you, then what will be the voltage for output voltage for 1011? So now examiner can provide you any output for any input, and they can ask you for any another input what will be the output voltage. What you have to do in this category of question? So easily within 30 seconds we can handle this category of question in GATE exam. What we have to do? Always you have to target first step size. So if you will write, sir, this will be nothing but this voltage will be del. Sir, this voltage will be 2 del. This is 0 multiplied anything 0. And sir, this is 8 del. So can I write this del, 2 del, 4 del, 8 del? So what will be the total step size of this? So sir, 1011 we can write 8 plus 2 plus 1. This is 11 del. So can you write, sir, this is 11 into step size. If you will find out step size, now from here you can also solve. Sir, this is del and this is 4 del. So you can write this is equal to 5 del. Can I write, sir, this is step size and this is 2 and this is 4 del. So 5 del is equal to given. So 11 del easily you can find out. So if they will provide you anything, what is your first target? First target, find out the step size. So step size means resolution voltage. In terms of voltage you have to find out. Sir, this is 1.25 by 5. 1.25 by 5. So from here, what is 11 del? So what is 11 del? 11 del you can put, sir, 11 into what is del? 1.25 by 5. This is the answer. This is volt. Okay, value you can calculate. So here, these basic things should be remembered. And all these basic formulas should be remembered. And now here question will come from for anyone output if examiner will provide it. If they will not provide, either they can provide this or they can provide this or they can provide this. If anything they will provide, first you have to find out step size. Now here this is 4-bit. Now if examiner will ask you, sir, what is your V reference and what is FSV? So here anything examiner can ask you. So here if examiner will ask you, sir, what is here FSV and what is V reference? So you can go with your basic formula. So you can go with your again formula. Already you have written here formula. So what is V reference? Number of bit is given. So from here you can also find out, sir, if 1111, it means this is 15 del. So this is nothing but 15 del is nothing but here full scale voltage. This is, sir, full scale voltage. In another way you can write, sir, this is 2 raised to power n minus 1 into step size 2 raised to power 4 minus 1, 15 del. In second way you can also write in this way. So what is the full scale voltage? Is 15 del. Full scale voltage is equal to 15 into step size. Step size you can put here. Step size is 1.25 divided by 5. Okay, so this is 5 and 3 into 1.25. Clear thing? So easily you can write. Now if examiner will ask you, sir, what is V reference? So V reference, you know very well, V reference minus FSV is equal to step size. So V reference is one step more than FSV. So you can also write FSV plus step size. This is the first answer. In second you can also write, so this is 2 raised to power n into step size. This you will get here 2 raised to power 4, 16 del. And del already you have calculated. So here V reference also you can find out. V reference you can write 16 into del, and del is 1.25 by 5, and this is 1. So if examiner will provide you number of bit, and for any input if they will provide you the output voltage, all the parameter you can find out. Now if examiner will ask you what is the percentage resolution. So here what is percentage resolution? So percentage resolution, okay, percentage resolution, either you can go with this or you can go with this. So in general examiner are interested in this, okay, but we have to concentrate. So with respect to whom you are writing here. The percentage resolution you can use, sir, this is 1 by, this is 2 raised to power n, means 2 raised to power 4, 16 into 100%. This is of V reference. In another way you can also write, sir, this is 1 upon 15 into 100% of FSV. So here two different answer can be possible. So we have to concentrate in this point. Okay, now sometime examiner will also do mistakes here. So this is that point is your bad luck. But we have to concentrate on this point. Okay, sometime Some examiner also consider both are same. Already this thing has been happened in GATE 2021. Okay, but don't worry, now they will not do the same mistakes. Okay, so this basic thing should be very much clear to you. Now the next important point here, next important point here, now examiner can ask question from here, monotonicity test. So from DAC, from digital to analog converter, okay, so first question examiner can ask you from this. I hope now we can handle. Now second question they can ask you from here, monotonicity test. So they can ask you from monotonicity test. Okay, and this is very important part. This is very important part. So generally two questions can be only framed from the digital to analog converter. And now next from the types of from digital to analog converter, and next question from the types of digital to analog converter. So sir, what is monotonicity test? Suppose you have designed a digital to analog converter. Suppose you have designed a digital to analog converter, and suppose we have here 4 bit. We have here 4 bit, and this is 4 bit. 4 bit D to A converter, and now I want to check you have designed correctly or this DAC is properly working or not. So what you will do? So here what you will do, just this output you will send to CRO. This output you will send to CRO. Here generally we will connect here one operational amplifier. Generally one operational amplifier, then this will send to the CRO. Sir, what is use of this operational amplifier? This operational amplifier will convert current output into voltage output. Okay, so this is the amplifier. So this operational amplifier will convert here current into voltage, So sometime in some diagram you will see operational amplifier. Don't get confused. There are no any use of that operational amplifier for you. Okay, so sometime they can connect operational amplifier here. Now our target is, if you want to check here this is working properly or not. So how we can check? So if I will connect here 4 bit counter, suppose if I will connect 4 bit up counter, and what is input of counter? Only clock. So what is the input of counter? Only clock. And now this output is connected to like this, suppose, and this is a 4 bit. And now if counter will start, so here you will get 0001. For 0001, initially this is 0. For 0001 you will get corresponding output. Then for 0010 you will get next output. 0011 you will get like this. So here exactly you will get a staircase. You will get a staircase till 16. So till 16 you can say till 16, and after 16 again you will get like this. Suppose this is 0, 1, 2, 3, 4, 5, 6, 7. This is last one is 15. Then after 15 again 0. 0 to 15 you will get at output, and corresponding voltage you will get that corresponding. So every will multiply by step size. So this is 1 step, 2 step, 3 step, 4 step, 5, 6, 7, 8, and last one is the 15 step. That is a full scale voltage. So this is the full scale voltage. You will get again 0. So you will get like this. So this is a monotonicity test. So sometime examiner will ask question from here. Okay, so sometime examiner will ask question from here. So here if I am going to take one question, I hope this thing is clear to all of you. Okay, so now if I am going to take one question from this monotonicity test. Okay, now okay, suppose if I am going to take one question from this monotonicity test. Okay, till now if anybody have any doubt, just ask me. Okay, so now come to the point. Suppose for example, if we have one 3 bit DAC, suppose 3 bit DAC, and this is 3 input. Okay, and DAC input I can say this is MSB. Suppose this is Q0. I can say the input, suppose this is I0, or you can write here D0. Okay, this is D0, this is D1, and this is D2. So this is MSB and this is LSB. Suppose for example, if somebody will use here, sir, 3 bit counter. So here either you can use down counter or up counter. If you will use down counter, so you will get this kind of output. You will get this kind of output. Okay, you will get this kind of output. Then again you will get this kind of output. Are you getting this point? So anyone you can use either up counter or down counter. So suppose if I am going to use here up a counter, suppose for example, and this is your clock. But if I will connect here this to this to this, and this to this, but if suppose by mistakes, suppose this is your Q0 and this is Q1 and this is Q2, if I will connect here, then what will be the output of this DAC? So will you get correct output? No, because this is MSB and this is LSB. So initially, suppose for example, this is 0. Initially this is 0. This question already has been asked in previous year GATE exam. So if initially this is 0, for the first clock, sir, this is 0 0 1, this is 1. So here for the first clock, sir, this is 0, sorry, this is 0 0 1, because this is MSB and this is LSB for the counter, and here this is LSB, this is MSB for the your DAC. So definitely you are doing a wrong testing here. So this monotonicity test is one kind of testing. Okay, by using this you want to check your DAC is perfect, or your DAC having some you can say some issue. So what I can say, for the first clock, sir, this is 0 0 1, for this 0 0 1, this is 1 0 0 4. So in the first clock you will get 4. Okay, you will not get 1 step, you will get 4 step. Okay, in the second clock, sir, this is 0 1 0, 0 1 0 means, sir, this is 0 1 0 2. So after 4 you will get 2 in the second clock. Okay, now in the third clock, sir, this is 0 1 1, but this is 1 1 0, so you will get here 6. So in third clock you will get 6. Now in the fourth clock, sir, in the fourth clock this is 1 0 0, but here this is 0 0 1, so you will get here 1. In the fourth clock you will get 1. Now in the fifth clock, sir, this is 1, this is 0, this is 1, and again here you will get 1 0 1. So this is correct. So in the fifth clock you will get a 5. Now in the sixth clock, here you will get 6, but here you will get 3. So you will get here 3. Here you will get 3. This is 3. Now in the seventh clock, this is 1 1 1, and you will get here 7. So you will get this kind of waveform. Again, this is start from 0 like this. Okay, so you will get this kind of waveform. In the CRO, suppose here this is a CRO. So you will get this kind of waveform in the CRO. So examiner can provide you here this output waveform, and they can ask you, or they can provide you 4 options, and they can ask you, okay, for what reason you are getting this waveform. So reverse question they can ask you, they can provide you this waveform, and they can ask you, okay, for what reason you are getting this waveform. So immediately you can see here you want 1 2 3 4 5 6 7, but what you are getting in place of 1 4. Okay, 2 is same, in place of 3 6, in place of 4 1 again, so in place of 4 2 1, and in place of 1 4. Now 2 is correct, 3 to 6, but here 6 to 3, and 5 is again same, and 7 is again same. So by this you can judge here MSB and LSB are interchanged. So what can be the answer? Here MSB of counter is connected with the LSB of DAC. This is the mistake. Clear this thing? So this kind of question can be asked from the monotonicity test. Clear this? So examiner definitely can ask question from monotonicity test. This is the first problem. Now, sir, is there any another problem can be happen? Yes, can be happen. Suppose for example, here in any way, suppose you have connected this connection, but by mistakes, suppose this is a loose connection. It can be possible. So any connections can be loose connections. Suppose if you will get any loose connection, so here you will get output, but here you will not get output. So suppose this is Q2, and suppose this is Q1, and this is Q0, and suppose by mistake this connection are loose connection, then what will be the output? So initially you will get 0 when you will apply first clock. Then now I have corrected this MSB LSB, both are perfectly connected. Then 0 0 1, you will get 0 0 1, one step size. So one step size you will get. Okay, this is one step size. Now in the second, so 0 1 0, but in place of 0 1 0 you are getting 0 0 0. So again you will get 0 0 0 means 0. Now in the next clock, here this is 0 1 1 3, but here you will get 0 0 1. So again you will get a 1. Again you will get a one step. Now again in the next 4, sir, this is 1 0 0. Again you will get here 1 0 0 means 4. So now you are moving to 4. Then here you will get 5 1 0 1. Again this is 1 0 1. So again you will get here this is 4 to 5. Then the next, this is 1 1 0, but this is not connected, so 1 0 0. So again this will reach to the 4. This will reach to the 4. And the last, sir, this is 1 1 1. So this is 1 0 1. So again you will get this is your 5, and then again this is 0. So you will get this kind of waveform if you will get one loose connection, and I have assumed this is the loose connection. So this can be the second problem for the monotonicity test. This can be the second problem for the monotonicity test. Now, sir, is there any another problem can be happened? Yes. So first problem can be happened, LSB, MSB can be interchanged. In second problem, any connections can be loose connections. Now the third problem. In third problem, this thing can also be happened. Suppose for example, if you have here 2-bit DAC, suppose we have here 2-bit DAC, this is D0 and D1, and but if 2-bit DAC is, if you are testing by 3-bit counter, suppose this can also be happened. Yes. And now if you have connected this to this and this to this, and now again you are not connected, both are not same, both output will be different. Suppose if DAC size is 2-bit, but if you are using here more size of counter, in another way we can also say, suppose this size is 3-bit, this is D0, this is D1, and this is D2, and suppose if you are using here 2-bit up counter, this can also be possible, this can also be possible. So here two conditions can be possible. I am considering this is 3-bit, and I am considering this is 2-bit, and now you are connected with this one. Okay, and this is Q0, Q1, and Q2. Then what will be the output? What will be the output? You can see initially output was 0, now 0 volt, now. Then after first clock, sir, this is 0 0 1. 0 0 1 means this is 0 1. 0 1 means one step size. So you will get here one step size. Now the next you will get in second clock 0 1 0. 0 1 0. This was 1, this is not connected. Both are 0 0. So 0 0 output will be again 0. So again you will get a 0. This is one step size. Again you will get a 0 step size. Now in the next 0 1 1. So for 0 1 1 you will get again 0 1. So again one step size. Again you will get one step size. Now in the next 1 0 0. This is 1 0 0. So here you will get 1 0. 1 0 means this is 2 step size. So this is 2 step size. In the next, sir, 5 1 0 1. This is 5. Again you will get here 1 1. So this is 3. So again one more step size. Now in the next, sir, 1 1 0. This is 1. This is 1 0. So here you will get 1 0. 1 0 means 2. So you will get here this step size is 2. Now in the last 1 1 1. So here you will get 1 1. So for 1 1 again you will get 3. And then it will reach to 0 like this. You will get like this kind of output. So this waveform is different, not staircase. This waveform is different, not staircase, and this is not staircase. In all the situation, your DAC is working properly, but your testing is wrong. Your testing process is wrong. In one time you have did loose connection here. In one time MSB and LSB of DAC and counter you have interchanged. And in the last situation, if DAC is 2-bit, then 3-bit counter you have used here. Are we getting this point? So this 3 category of questions can be framed from here. Okay, so this category of question can be framed from here. Okay, so this category of question can be framed from here. Okay, so this is the second situation or second things from where examiner can ask question from DAC. So just confirm me this thing is clear to all of you or not. Okay, then I will move towards the types of DAC. So only 3 category of question can be framed from the DAC. Okay, 3 category. Okay, later I will also discuss some more interesting question from the DAC. I hope this thing is clear to you. Now I will jump to the types of DAC. Okay, so next one is a types of a DAC. So types of DAC, definitely I hope everybody know, because from here question can be asked from network theory, and same topic also we have also discussed in the analog circuit and also in the digital electronics. So these types of DAC, okay, network theory you can also this topic or come under the analog, or this topic or come under the digital. Okay, so now I hope this thing is clear to all of you. Okay, now come to the point. So we have 2 types of DAC. Everybody know how many types of DAC? 2 types of DAC. First one is weighted resistor type. This is a weighted resistor type. Weighted. Okay, this is resistor type. Electrical resistor. Okay, so type. And second one is a R2R. This is first one. And second one is a R2R. And this is ladder network. So R2R ladder type DAC. So two types of DAC in real life. Here many number of resistances required. That's why we will not use. In real life always we use R2R ladder type DAC. That's why examiner will only ask you question from the R2R ladder type DAC. Okay, so examiner will ask you question from R2R ladder type DAC. Okay, ladder type DAC. So just I want to tell you, we can use here one op-amp, and suppose this is ideal op-amp I am going to use, and suppose if I am going to use this is a voltage follower. So here what output you will get? You will get at output. So this is the actual circuit. Okay, this is a voltage follower. Already I tell you here in last we can use a op-amp, and that op-amp exactly can convert current to voltage or voltage to voltage or voltage to current in this way. Okay, so practically there are no any use of this op-amp in general. Okay, so now here suppose we are considering one R, here 1 2 R, here 1 R, here 1 2 R, suppose here 1 R and here 1 R. Now the important thing is, if first you should know one thing, all this horizontal resistor R, this is 2R, this is 2R, and all this vertical R, this is R, this is R, this is R, and this is, and last one is grounded, and last one is always grounded. This is important thing. Last one is always grounded. So now second important thing, sir, last one is grounded, then remaining this is 1 bit, this is 2 bit, and this is 3 bit. So this is 3 bit DAC. So first you have to see how many bit DAC is given. So what you will do, last R is connected to ground, and remaining R, and this is 1 bit, 2 bit, and 3 bit. Now sir, which is MSB, which is LSB? So this is nothing but 3 bit DAC. 3 bit DAC, this is nothing but 3 bit DAC. Which is MSB and which one is LSB? This is very important thing. Which one is MSB and which one is LSB? So here this voltage, this bit is LSB. This is very important, and this first one is MSB. Always you remember first one is MSB, then last one will be LSB. So you can write this is D0, this is D1, and this is D2. This is D2. Okay, and how you can find out this voltage? So by using superposition theorem. So you can consider this is first voltage, this is second voltage, this is third voltage. So how you can handle this question in GATE exam? So you can apply this D0, D1, D2. So in digital this can be either 0 or 1. But examiner sometime can ask you question from here. They can provide you this voltage different, this different, this different. Sometime they can also use negative voltage. Sometime they can use positive voltage. Sometime anyone can be here ground or 0. So just you have to apply here superposition. If here voltage given, here voltage given, here voltage given. So how you can find out the answer? So you can see, if for D0 if you want to find out, both will be ground. So this complete circuit should be converted into Thevenin equivalent. So here you will get this voltage half here. So I am not going with the solution, just I am going to the direct process. If this is D0, here you will get half voltage D0 by 2. Then in next step this is D0 by 4, and here you will get D0 by 8. So here you will get D0 by 8 voltage because of this. Because of this, what Thevenin equivalent you will get, and all the voltage is 0. R, this is 2R, this is 2R, this is R parallel. Okay, sorry, we did wrong here. Sir, this resistor is R, this R, and all this parallel resistor are 2R. Correct this. All the series resistor are R, and parallel, and your vertical horizontal resistor are R, and you can say vertical resistor are 2R. Please correct this. Okay, so now if all these are 0, so we can find out here resistance, equivalent resistance 2R, R are 2R, then 2R, R, then R 2R, then 2R parallel. So always equivalent resistance here you will get R. So for this D0 directly here you will get D0 by 2, D0 by 4, D0 by 8. So here voltage, because of this, suppose if D0 is 5 volt, so here you will get 5 by 8. If D0 is minus 2 volt, so here you will get minus 2 by 8. If D0 is 0 volt, so here you will get 0 by 8. Are you getting my point? So this is D0 by 2, D0 by 4, D0 by 8. Okay, and this is a voltage follower. So if what is this V0? So V0 directly you can write, because of this D0, your output voltage will be, sir, this is D0 by 8. plus. Can I write? Now, because of this, here this is d1 by 2, d1 by 4. So, in every step, divide by 2, divide by 2, divide by 2. So, here you will get, sir, this is d1 by 4. And then here, this is a d2. So, here you will get a d2 by, sorry, d2 by 2, like this. Okay, so don't remember direct formula. In GATE exam, you can solve in this way. Okay, in GATE exam, you can solve in this way. So, B0, you are getting it. Suppose, for example, this is 1, this is 1, this is 1. Suppose, for example, this is 1, this is 1, this is 1. So, what you will get? Here you will get, sir, this is 1 by 8 plus 1 by 4 plus 1 by 2. 1 by 2, 1 by 2. You hear the thing? So, here you will get 1 by 8 plus 1 by 4 plus 1 by 2. Clear this thing? So, this is, you are getting 7 by 8. So, what you are getting here? 7 by 8. Okay, so like this you can solve. Any voltage examiner can provide you. So, definitely questions can be asked from here. I hope this thing is clear to all of you. Now, you can handle, and already I hope you have studied this thing. This is op-amp, and op-amp, and this circuit, you can also solve by network theory, and this circuit you can solve by your analog. So, in GATE exam, suppose if directly you cannot solve, then what you can do? This complete network, this is your network theory. This complete circuit you can solve first by the network theory, and that you can connect here. So, Thevenin equivalent of this complete circuit you can find out. Thevenin equivalent of this complete circuit you can find out, and then you can connect here. And this basic operational amplifier you can solve. Sometime this complete block is also connected to, this is positive and this is negative terminal. This is non-inverting, this inverting terminal. Sometimes this block is also connected with inverting terminal, In that time, this process can be changed. So, what should be the basic process? If questions came from this design, so directly here you can write this is divide by 2, divide by 2, divide by 2. Clear? But if different design of question you will get. So, what you have to do? First, you have to solve this by network theory, and then this you have to solve by operational amplifier. Okay, so here don't be wrong. Okay, so I hope definitely you can handle this category of question. Okay, so this is your R2R ladder type DAC. R2R ladder type DAC. Okay, definitely examiner can ask question from here. Examiner will not ask you question from weighted resistor, because here only 2 resistor we are using in weighted resistor. So number of resistor we have to use R. Okay, 2 raised to power 1 R, 2 raised to power 2 R, 2 raised to power 3 R, 2 raised to power 4 R. So many number of resistors we have to use in weighted resistor type. Okay, so I hope this thing is clear to all of you. Okay, so if anybody has a doubt till now, please respond everyone. Okay, everyone please respond. Okay, now I am going to take one good problem from here. Now here, suppose we want to implement here. Now in GATE exam, which kind of question will be asked by the examiner? Now you can see. Suppose if you want to implement, 8-bit DAC. Suppose we want to implement 8-bit DAC, but we don't have 8-bit DAC, but we have 4-bit DAC. Okay, so here implement 8-bit DAC by 4-bit DAC. 4-bit DAC. Okay, so this is a gate level question. So in GATE exam, they will ask you in this level of question. Okay, so now I hope this thing is clear to all of you. We can handle this category of question. Okay, now, so here, sir, how we can implement 8-bit DAC by using 4-bit DAC. 4-bit DAC. Okay, so now, so one question I am going to consider from this topic, and this is a previous year GATE question. So in previous year, one question has been asked. So one operational amplifier is given. This is plus, this is minus, and this is the output voltage. Here in your inverting terminal, when this feedback resistance is given, this resistance is 8 kilo ohm. This resistance is given 8 kilo ohm. Okay, and now this positive terminal, or you can say non-inverting terminal, connected to ground. Now here 2 resistor is connected in this way. 2 resistor. Okay, this is 2 resistor. Okay, and now here one 4-bit DAC. This is a 4-bit DAC is connected, and here 4-bit DAC. This is 4-bit DAC is connected, and here this is 4 input. Here this is 4 input. So this is D0. This is D1. This is D2. This is D3. this will be D4, this will be D5, this will be D6, and this will be D7. This circuit is given. Okay, now one resistor also they have provided. This resistor is 8 kilo ohm. This resistor is 8 kilo ohm. And now they have said, so this voltage is output of this DAC is V01, output of this DAC is V02, and this resistor is R. This resistor is R. Okay, so this is the design. Actually, this is the design. You have 4-bit DAC, but if you want to implement 8-bit DAC, so this complete circuit you can say, sir, this is V0. This complete circuit operation will work as a 8-bit DAC. Then what will be the value of this R? Are you getting my point? So this complete circuit, if work as a 8-bit DAC, this is a 8-bit DAC, and this this 8 input, this is 4, 5, 6, 7, 8, and this is your output voltage V0. Okay, so here examiner asking, you can say this you can feed into this block. You can say you can feed into this block here. So this is the circuit, 8 input and 1 output. This is your decimal input, or you can say binary input. This is binary input, and this is analog voltage. So what will be the value of R? What will be the value of this R? So that this circuit will work as a 8-bit DAC. Any student can tell me the answer of this. Any student can tell me answer of this. This is a gate level. This is a level of gate. This is a level of gate. This is a level of gate. Just tell me. Just tell me. I am waiting for your answer. Here I am waiting for your answer. I am waiting for your answer. This is a level of gate. Okay, here this is 4 options they have provided. No, here this is numerical answer type. This is numerical answer type. This is numerical answer type. So kilo ohm. So R in a kilo ohm. R in kilo ohm is equal to question mark. What will be this value of R? 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 So if you can say, sir, this is connected with inverting terminal. So you know very well, minus of. So for this output, sir, minus of 8 by 8 into V01. You can write, okay. So for all this block, so you can say, sir, this is minus 8 by 8. So this is multiply with 1. So for this, all this D0, D1, D2, D3, so you will get minus 8 by 8, means you are getting inverting output. Okay, but no worry. Just here, this all the 4 output is going to multiply with factor 1. Factor 1. So suppose, for example, for D0, suppose I can assume 1 volt. Suppose this is total 8 bit, and see here if I will assume step size is 1 volt. Suppose, for example, here n is equal to 8 bit. Here n is equal to total 8 bit. But in this DAC, this is 4 bit. So if this D0 is 1, okay, if this D0 is 1, 0, 0, 0, 1, what should be output voltage? Output voltage should be 1. Are you getting my point? So if this D0 is 1, this output voltage should be 1. Okay, if all the if all these 4 are 1, 1, 1, 1, output voltage should be 15 volt. Clear? Now, so what I want to tell you, if I am considering this 8 bit, suppose 8 bit, if I am considering this is your D7, this is D6, this is D5, this is D4, this is D3, D2, D1 and D0. Okay, like this. Suppose if D3 is 1 and this is 0, 0, 0. So in this situation, you can divide this into 2 parts. So if D3 is, sorry, if D0 is 1. So what should be the output voltage? 1 volt. If I am considering step size 1. So this should be 1 volt. Now suppose if this D4 is 1. If D4 is 1, then what should be the output? Then what should be the output? This is del 1, this is 2, this is 4, this is 8, this is 16. So output voltage should be 16 volt. This should be 16 volt. So if this value is 1, then output voltage should be 16 volt. It means, what can I say? What is a multiplication factor in this block and what is a multiplication factor in this block? So if this is 1, so here V02 you will get 1 volt. V02 you will get 1 volt. But what is your requirement? My requirement is 16 volt. How you will get 16? So minus of this 8 by this R should be is equal to 16. So if you are considering R is equal to 1 by 2 kilo ohm, or you can say 0.5 kilo ohm, then what will happen? So for this you will get 1 volt, but at output you will get 16 volt. Similarly for this you can also check. So what I can say, if suppose for example, if this is 0010, you will get 2 volt. So for this 0010 you will get 2 volt. But if this is 00 here, if this is 10, if here this is 10, then this is 1 2 4 8 16 32, then your output should be 32 volt. It means multiplication factor is 16. Multiplication factor is 16. So 2 raised to power n is the multiplication factor. So from this here 2 raised to power n should be the multiplication factor, and n is this 4 bit. So you can say, so 16 is the multiplication factor. So if this is 1, this is 1, what should be output voltage? 2 volt. So if this is 2 volt, this 8 by 1 by 2 means 16, 16 into 2, you will get here 32. So what should be the value of R? R should be 1 by 2 kilo ohm. Clear this point? So this category of question definitely can be framed in GATE exam. I hope now you can handle this category of question. So one more design. Okay, now reverse question if I will ask you. I hope this thing is clear to all of you. Now if I will ask you here reverse question, suppose you have to implement here 4-bit DAC. Suppose if you want to implement here 4-bit DAC by using 2-bit DAC, suppose for, okay, so how you can design? So you can consider here one operational amplifier, and again here so this amplifier will provide you multiplication factor. So if you have here two number of 2-bit DAC, this is 2-bit DAC, and again this is 2-bit DAC, this is 2-bit D to A converter, 2-bit D to A converter. So here this is 2-bit. I can say, sir, this is D0, D1. You can say this is D2 and this is D3. This is D3. Can I say, suppose if this resistor is suppose R and this resistor is suppose R. Suppose, then what will be this resistor? So here for this multiplication factor is 1. Yes, definitely 1. So for this block multiplication factor should be definitely 1. So what will be here multiplication factor? So here multiplication factor should be, so this complete block should be multiplied by 2 raised to power n, and here n is 2. So this block should be multiplied with 4. So here what should be your amplification factor? That should be 4. So if this is R, so you can write here this is nothing but R by 4. This is nothing but R by 4. So minus R by R by 4 minus R by R by 4 is equal to 4. So all this output will multiply with 4. So how you can write, sir, what will be this resistance value? This resistance value will be, first thing you remember, sir, this by this multiplication factor from here should be 1, and what should be multiplication factor here? If this is R and this both will be same, so if this is R, so what will this, sir, R upon 2 raised to power n. Can I write? And what is n here? This LSB, this is 2-bit D to A, means you can say this is LSB DAC and this is MSB DAC. Okay, and both the n bit is same. Thus you can put here 2 raised to power n, and n is here 2. That is R by 4. That is R by 4. So like this you can handle. This is a very, very good design. So this category of question can be asked in GATE exam. Okay, so I hope from DAC, generally examiner can target question from the basic. They can provide you any input and they will provide you output for that, and for another input they can ask you the output, and they can ask you question from V reference or FSV or resolution voltage, and second they can ask question from monotonicity test. Okay, already 3 cases in general. There are so many cases also can be possible. So now you can judge that. And now the third category of question they can ask from the this R to R ladder network. And now this is fourth category of question. They can also ask you question from implement big size of DAC by using a small size of DAC. So you can see the level of GATE question. Okay, so I hope this thing is clear to all of you. Okay, so everyone, I hope this thing is clear to all of you. I hope this thing is clear to all of you. Okay, so please just confirm me. Okay, this design is clear to you or not? So please just confirm me. This design is clear to you or not? Then I will start ADC. Okay, then after I will start ADC. Please just confirm me first. Okay, and just confirm me first. Okay, now. Okay, please just confirm me first. DAC is clear to all of you. So this 4 category of question, okay, can be framed from the DAC. Okay, now so next topic we are going to start, that is analog to digital converter. Okay, but if you will ask me, sir, what is a more probable chance examiner will ask question from either DAC or ADC? So definitely chances are more for ADC. Definitely chances are more for ADC. So you can say 2 year they will ask question from ADC, 1 year they will ask question from DAC. Okay, so now the next part I am going to start, that is ADC. That is ADC. Okay, please everyone. Okay. So have you studied this? How we can implement big size of ADC? Oh, sorry, big size of DAC by using small size of DAC. Okay. So this is very good topic. Now come to the point. Next topic is ADC. We can say analog to digital converter. Analog to digital converter. So here I am not going with block diagram. I hope you have studied at least one time block diagram. Just I will revise all the thing and I will connect all the things so that you will remember all the formulas and all the concept, and easily you can handle in GATE exam. Okay, so here I am going to connect all the things. Okay, here I am going to connect all the things. So here sir, first important thing is here, so first important parameter is here conversion time. Here conversion time. So here first important parameter is conversion time, and conversion time will be always multiply with number of clocks. So conversion time will be nothing but conversion time is suppose 6 clock, 5 clock, 10 clock. So anything, so any parameter k into clock time period into t clock. This is a conversion time. So we can say how many number of clock is required to convert from analog to digital converter. So this is nothing but how many number of clock. So we have to find out for each and every type how many number of clock is required to convert the data from analog to digital converter. What should be the your block diagram? Your input will be analog input, and I can say this is n bit ADC. This is n bit ADC. You can again consider here V reference, and if for maximum voltage you will get your output 11111. Okay, now so here you will get this is the your binary data, if this is n bit ADC, so here this is a total n bit binary data. Okay, so this is n bit analog to digital converter. Okay, again here everything is same, sir. What is FSV? Okay, what is V reference, and what is step size? This basic thing is same here, but here two important thing we have to discuss. First thing is, sir, what is the conversion time? And second important thing is the what is the quantization error, and second one is the when you are doing analog to digital conversion. So here one process is called quantization, and only one error we will get in analog to digital conversion, that is the quantization error, and that nobody can remove. Quantization error cannot be zero in any situation, nobody can do. So this is a basic problem with analog to digital conversion. Always you will get quantization error, and we want to reduce, always what is our target, we have to reduce that quantization error, but this cannot be zero. So second is the what is the quantization error. Sometime examiner are only interested in error, but just I am going to write here, sir, what is quantization error? Or you can say what is the error, maximum possible error. So quantization error you can write this is QE. So here we are interested in what is maximum quantization error. So we are interested in Q max. QE max. Now one important thing I want to ask you. Suppose we have two level. Okay, this is level 1. This is level 0. Suppose we have two level. Suppose for example this is 0 volt. Suppose for example this is a 2 volt. this is 2 volt, this is 2 volt. Okay, now so this step size is here 2 volt, this step size is here 2 volt. Now suppose for example, if your input is like this, if your input is like this, and always you are getting upper value, always you are getting upper value. Suppose for example, so for this error will be this one, and for this again error will be this one. Suppose if this value is you are assuming 2 volt, and this value if you are assuming this, so what can be the maximum error? And this is your step size. Suppose I am saying this is your step size. So in this situation, so every in between any value from 0 to level 0 to level 1, that is quantized to upper portion, or you can say upper level. So every value is going to be quantized to the upper level. So what you will say here, what is QE? Quantization error maximum. So maximum quantization error is del. Can I say? Now in second way again, suppose again we have two level, again we have two level, and now if any value between here, this is suppose 0 volt, this is 2 volt, any value between these two is quantized to the lower level. So if any value are here, then this is quantized to here, so this is the error. And suppose if you are considering this, so here this is the error. So in this situation, so what is the maximum quantization error? So in this situation, QE max. In this situation, what is again QE max? So maximum error can be this, and this is step size. Again here del. So what is difference between these two del? So here error can be positive, so you will say here error is negative. If you will say sir here error is negative, so here is error is positive. So there are some confliction. Some student will write what is a quantization error formula. Okay, so actual value minus measured value. Some student will read measured value minus actual value. So anything you can write here, so no worry. Examiner are not interested in the minus or plus. Examiner are interested in the value quantity. So here just I want to tell you, if you will do any value quantized to the upper level, so you will get here quantization error, maximum quantization error, this is del. And what can be the minimum? Minimum can be 0. And here again maximum quantization error can be del. Now suppose third category, in third category, suppose this is 0 volt, level 0, and suppose this is first level. Suppose for any value, this is a center value, suppose this is a center value. So what I can say, this value is del by 2, and what is this value? This value is step size by 2. So if any value between 0 to 2 is quantized to the center, suppose if you have here any value, this is quantized to the middle level. Suppose if we have one value here, this is quantized to here. So for this two, what is the maximum possible error? So for this maximum possible error del by 2, and for this maximum possible error del by 2, but this is practically plus minus del by 2. So here what you will write, suppose here I am considering suppose this is minus del, so I can write this is plus del, but anything you can assume. You can also assume sir here this is plus del, this is minus del. Okay, then sir what will be the here QE max? So here quantization error max will be plus minus del by 2, plus minus del by 2, here plus minus del by 2. Okay, so here two thing is very important. First thing is the conversion time for every types of ADC, and second thing is the sir what is a quantization error, maximum quantization, maximum possible quantization error for that type of ADC, So in every time I am not interested in direction plus or minus, I am interested in either del or del by 2. Only two category of quantization error can be possible, only two category of. But when you study this topic in communication system, always you consider quantization error is del by 2. But this will be depend which type of ADC you are using here. Which type of ADC you are using here. Are you getting this point? Which type of ADC you are using here. Which type of ADC you are using here. And I promise you, many students are getting wrong in this situation. So if I will ask you the type of ADC, so some students are going to be wrong in this point. Okay, so how many number of types of ADC? Anybody can tell me how many number of types? So generally we study 5 types of ADC, generally we study 4 types of ADC. Okay, so how many types of ADC? So this thing should be very much clear to you. So we have to find out conversion time for all the ADC, and second What is the quantization error for? This is maximum quantization error for all the ADC. Okay, now if you can see here, sir, error is del, error is del. Here also error is del. Here you are considering one side. Here you are considering one side, but here you are considering both sides. So actual error is same, but representation is different. But this will be beneficial for us because quantity is going to be less. Always magnitude of the error is, you are reading here, del by 2. But here magnitude of the error is plus a del, and here magnitude of the error is del. So definitely in real life we can go with this one. Okay, so in communication system always we use what is the quantization error, that is maximum plus minus del by 2. But here you cannot write always plus minus del by 2. Here it will depend on the types. So here all the question in GATE exam you will get from the type. So we have to study here 4 type of ADC. So how many types of ADC? How many types of ADC? There are so many types of ADC, but for GATE exam 4 types of ADC is required. First type is counter type. First type is counter type ADC, counter type ADC, counter type ADC, and this is also called ramp type. This is also called ramp type. This counter, or you can say RAM means slope. So this counter type or ramp type. Now the second type is a successive approximation. This is successive approximation. Successive approximation type ADC. Successive approximation. Now number third is a flash type. So this will be fast because the name is flash type. So this is flash type. And now the number four is a dual slope, and this is also called integrator type. This is called dual slope. This is called dual slope, and this is also called integrator type. This is also called integrator type ADC. This is also called integrator type ADC. Now I will ask you here, if you remember, okay, I will discuss. If you remember, sir, what is the maximum quantization possible error in counter type ADC? Anybody can tell me? I am waiting for your answer. Sir, what is here maximum possible error? Sir, del or del by 2. I am not interested in minus or plus. I am interested in, sir, what is maximum possible error? Del or del by 2. What is for this number one counter type? What is for number one? Del or del by 2? Okay, tell me. Many students are getting wrong in this situation. Again, I am telling you, what will be the maximum possible error here? Del or del by 2? Tell me. Del or del by 2 for the first one. For the first one, del or del by 2. Tell me, del or del by 2? I am waiting for your answer. What will be the maximum possible error, quantization error maximum for counter type ADC? For counter type ADC. Tell me. I am waiting for your answer. What you feel? Just tell me. Okay, this is del. Okay, now del. Now, so here, what is the maximum possible error? Here, this is del. Here, this is del. Now, what will be for successive approximation? What will be the maximum possible error for successive approximation? Number 2. What will be for number 2? What will be for the number 2? So, maximum possible error for the number 2. Maximum possible error for the number 2. What will be the maximum possible error here? What will be the maximum possible error here? Again here maximum possible error is 10. Remember, again here maximum possible error is 10. Now in flash type, again here, sir, maximum possible error is 10. Again, sir, then what will be in dual slope? In dual slope, maximum possible error is 10 by 2. So here maximum possible error is 10. So you remember first this thing. Many students are getting wrong in this situation. Okay, now. So first type, I want to discuss first type. First type is a ramp type. This is a ramp type. And this ramp type, you can also say, this is a, you can say, counter type. This is a counter type. This is a counter type. So block diagram, I am not going with the block diagram. Just I want to tell you the process. So here in counter type, suppose we have here 3-bit count. Suppose 3-bit. Suppose we have here 3-bit ADC. Suppose if we have here 3-bit analog to digital converter. Okay, now analog to digital converter. And suppose for example V reference I am going to assume 8 volt, and here FSV is 7 volt. So if FSV is 7 volt, means input cannot be more than 7 volt. Are you getting this point? So that's why here this V reference is not much required. So practically we are not interested in here this V reference. So here full scale voltage is 7 volt. So you cannot apply more than 7 volt to this DAC. Okay, now, and if n is 3 bit, so what this counter type will do? So it will start from 0 0 0. So it will start from 0 volt, then it will reach to 1 volt, then it will reach to 2 volt, then 3 volt, then 4 volt, then 5 volt, then 6 volt. Okay, this is 6 volt and then 7 volt. So your input maximum can be between 0 to 7. So your input will lie anywhere. Suppose I am assuming my input voltage is, here 6.1 volt. Suppose this is your input voltage. Suppose this is your input voltage, analog input, and this you want to convert into binary, because analog to digital converter. So your input voltage is 6.1 volt. So 6.1 volt, you will get here 7 volt, and 7 volt binary. So this binary you will get, sir, this is 0 0 0, sir, this is 0 0 1, because this is 3 bit 0 1 0, sir, this is 0 1 1, this is 1 0 0, this is 1 0 1 1 1 0 and 1 1 1. So if we have one 3 bit ADC, which kind of, this is very important. If I am writing ADC, which type of ADC? Sir, this is a RAM type ADC. So this is a ramp type ADC, and here this is a analog input. So analog input. So according to analog input, what will be the your binary output? Suppose this is 3 bit, this is D2, this is D1, and this is D0. So here first, here you can also write, suppose if you know the FSV, I am not writing here V reference, I am writing V reference. Okay, so sorry, I am writing here FSV. So at maximum FSV you can apply. Important thing, more than FSV you cannot apply in this category of circuit. Okay, so more than FSV you cannot apply here. So maximum output voltage can be 1 1, maximum output binary can be 1 1 1. Now here one important thing, always one important point, remember, always your output binary will be more voltage, always more voltage. So if you have 6.1, so your counter will stop at 7, this thing you remember. Clear my point? Many students don't know exactly this. Okay, and many students are getting trapped in this situation. So for the counter type, you remember, always your output voltage will be more than that. Clear the thing? So always your output voltage will be more than. So here you can write, sir, always output voltage will be more than input voltage. Clear this point? So always in upper side it will stop. Means here if this is the input voltage, so always at upper portion it will be stopped. What can be the maximum possible error here? Step size. So can I write here, sir, quantization error maximum can be possible here, step size. Or here remember, output voltage is always greater than input voltage. So if you are getting here 1 1 1, so corresponding to 1 1 1, your result is 7 volt. But what was your input? Input was 6.1 volt. So that's why I am saying your output is always more than this. This is very important. Examiner can target this point. If examiner will ask you the same question, suppose here I am going to write. So in RAM type, suppose for example, if examiner will ask you same question in theoretical way, suppose if we have n is equal to 3 bit, okay, and full scale voltage, either they will provide you full scale or V reference or step size. So you can find out if step size is known, full scale voltage and V reference you can find out. If V reference is given, FSV and step size we can find out. If FSV is given, we can find out step size or V reference. So any three value are related with each other. So if they will provide you any one value, you can find out all the value. V reference you can also find out, and step size you can also find out. Clear this thing? So if any value, if they will provide you any one. So here I have provided FSV is equal to suppose 7 volt. Suppose 7 volt. So you have to first find out step size. Now what is step size? Sir, step size will be this will be 1 volt, and V reference will be, sir, this is nothing but 8 volt. All the value you can find out. Now they have provided number of bits and this thing. Now they will, if they will provide you, sir, if input voltage is, if here V in is equal to, if V in is equal to suppose 4.3 volt. Suppose this is 4.3 volt. Then what will be the corresponding binary? Then what will be the D2, D1, D0? Then what will be the corresponding binary? Some student will write answer here 4100. Some student will write here answer 5101. This is the mistakes. Some student will stop at upper portion. Some student will stop at lower portion. So you should know about the exact design. RAM type, in RAM type, where this RAM type will stop. Always this will stop at upper portion. So your output voltage cannot be. So just you can find out the next level. So next level voltage is 5 volt, and 5 you have to write in the binary. So 5 according to step size we have to write here. Step size was 1. That's why directly I can write here this output binary will be 101. This thing is the answer. Clear this point? I hope now you can handle this counter type. Now this is the first point. So if examiner will provide you any input, so where this will be stopped and what will be the binary, right? Sir, what is a quantization error maximum? Can we write? Now the second important thing, conversion time. Sir, what is the conversion time here? What is conversion time? So it will depend on the input or not depend on the input. First important thing here, conversion time is depending on the input or not depending on the input. Yes, definitely. Sir, if input is your 1.3 volt, so only 2 step is required, so 2 clock is required. So for the first clock this, for the second clock this, for third clock this, for 4, 5, 6, 7. So you can say for 3 bit maximum 7 clock is required. So and conversion time is depending on the input voltage. So here what is the conversion time? So if I want to write conversion time TC, so what can be the TC? Nobody can tell the formula for TC. Yes, but for maximum conversion time you can say. So what is a maximum conversion time? So sir, maximum conversion time can be 2 raised to power n minus 1 into t clock. Can I write? So how many clock can be required for n bit 2 raised to power n minus 1 into t clock? And now the next important thing you remember, conversion time is directly proportional to. So here I can write, sir, conversion time is directly proportional to. Okay, so conversion time is directly proportional to V is input voltage. So conversion time will depend on the input voltage. Conversion time will depend on the input voltage. So here conversion time is variable or fixed parameter? Variable. Remember, conversion time, if V in will be changed, conversion time will be changed. So conversion time is a variable parameter. Clear this point? So and also this will depend on the number of bit. So for more number of bit, conversion time will be more. So in real life, for you can say 4 bit, 5 bit, 6 bit, we cannot go with this counter type because this is slow. What is the disadvantage? So for more number of bit, definitely this will be slow. Definitely this will be slow. Okay, so this is a very, very important thing. I hope every point I have cleared here. Okay, where this will stop, what will be the exact binary value. So here in digital to analog converter or analog to digital converter, generally students are getting wrong because of only these two situations. What will be this answer? Some student will write 101, some student will write 100, but 100 is the wrong choice here. Clear this point? So now come to the second one. Sir, successive approximation. So in every types of ADC, you should know exact what will be the output. It will stop to upper portion or it will stop to the lower portion. First thing. Second, sir, what will be the corresponding binary value? Okay, and sir, what will be the quantization error maximum and what is the conversion time? And conversion time is a fixed or conversion time will depend on the input voltage. Clear this point? Now the second one. Okay, second I am going to take second type. Second type is a successive approximation. Second type is a successive approximation. Okay, I hope this thing is clear to all of you. Okay, now the second type is a successive approximation. So here we can write conversion time. So what is here conversion time? So conversion time you can write 2 raised to power n minus 1 into t clock. You can write 2 raised to power n minus 1 into t clock. 2 raised to power n minus 1 into t clock. You can write in this way. Okay, now the second. Now come to the second. Successive approximation. Successive approximation. Successive approximation. Second one is a successive approximation. Okay, successive approximation type ADC. Second one is a successive approximation type ADC. Okay, sir, now I am able to do PYQ also after your PYQ, all the question easily you can handle. Okay, now sir, in successive approximation, so anybody can tell me, already error I have provided, so anybody can tell me where in this situation where output will be stopped, where output will be stopped. What is exactly meaning of successive approximation? Suppose for example, if we have here, suppose for example, n is equal to 4 bit. Suppose I am considering n is equal to 5 bit. Suppose del is equal to 1. Okay, 1 volt. And step size is so here what is V reference? Sir, V reference will be 32 volt. V reference will be 32 volt. And sir, what is FSV? And sir, FSV will be here 31 volt. And full scale will be 31 volt. Okay, so you will get this thing now. So what you will do here? So first you will reach to here. First you will reach to V reference by 2. So here, if suppose this is n is equal to 5 bit, step size is 1. So can I write, sir, 1 meaning is 31 volt. 31. Okay, sir. Now 1 0 0 0 0 meaning is V reference by 2. Sir, this is 16 volt. Or you can write, sir, 1 2 4 8 16. Can I write? Now, sir, 1 1 0 0 0 meaning is 32 plus 8. This is 1 2 4 8. So 16 plus 8. So 16 plus 8 is, this is 24 volt. Can I write? Now, so in same way, so we will start from this situation. I am not going with the diagram. Diagram is not required for the GATE exam, and I hope definitely you have studied the diagram. Now come to the point. So in successive approximation, suppose if this is the situation, what you will do? So first, from starting, we will reach to, at starting from where you will start. I will start from 1 0 0 0 0. So you will start from 1 0 0 0 0, and this corresponding voltage is 16 volt. So always you will start from 1 0 0 0. Here ring counter we will use. Okay, so we will start from 16 volt. Now you will check your input is more than 16 or less than 16. Now you will check your input is more than 16 or less than 16. This is the important one. Suppose I am going to assume here my V in is, suppose my V in is here 29.2 volt. Suppose here 29 point, suppose I am assuming 29.7 volt. Suppose my V in is 29.7 volt. So you will check your input is more than 16 volt or less than 16 volt. It is more than 16 volt, and corresponding this binary is, this corresponding binary is 1 0 0 0 0. So now you have to go up. If you want to go up, this bit will be fixed to 1. This bit will be fixed to 1. This bit will be fixed to 1. Now what you will do? You will jump to the next, and again you will check. So now here you will jump, and this is nothing but this is 1. And what do you meaning by this? Sir, this is 1 1 0 0 0, and this meaning is 24 volt. So now you will reach to 24. Then again you will check. Your input is more than this or less than this. Sir, this is more than this. So if this is more than this, it means again you have to go up. Okay, so where you will go? So now we will jump to 1 1 1 0 0, and 1 1 1 0 0 means this is 16, this is 8 24, and this is 4. 24 plus 4, this is 28 volt. Sir, this is 28 volt. Again you will check. Your input is more than this. So again, if this is more than, again you will jump to the upper level. So again you can say, sir, this is 1 1 1 1 0. It means this is 16 plus 8 24, 24 plus 4 28, and this is 30 volt. So now this is 30 volt. So if this is 30 volt, what do you mean by this? It means again you will change this bit to 0. So if you have jump, and now if you have crossed this input voltage, so this bit will change to 0. This bit will change to 0. This remaining bit was 111, but this bit is changed to 0. Now again, what you will do, 11101. So every bit you are checking. So in this, what we are doing, this bit we are checking. So if you are increasing here, so this bit will fix to 1. Again, if you are increasing here, so again this bit will fix to 1. Again, if you are increasing here, so this bit is fixed to 1. But here you have to decrease. So if you are decreasing here, so this bit will change to 0. Okay, so 1110, and now last bit you will do 1. So 11101 means sir, this is 28, sorry, 16 plus 8, 24, and for 28, and this bit is 29. So now you will reach to 29. You will reach to 29 volt, and 29 means sir, this is 111, this is 0, and this is 1, and this is 29 volt. This is 29 volt. Now you will see here, your input is more than this or less than this. Now you will see here, your input is more than this or less than this. This was your input. This is 29.7 volt. This is 29.7. It means your input is upper. If your input is more, so this bit is fixed to 1. So this bit is fixed to 1. Okay, this bit is fixed to 1. So what will be the final output? 11101. 11101. So your result is 11101. Clear this point? So how many clock is required? You are going to start from here. First clock, second clock, third clock, fourth clock, and here 5 clock is required. 5 clock is required. Here 5 clock is required. So how you can write here? Just I am going to write here states. Here how you can write the states. This is the important point. So here the important thing is, can I remove this? So your input was 29.7 volt. So here first you will write, sir, start conversion. Start conversion. Start conversion. Okay. So if you will start conversion, okay, now your initial state is 10000. This is initial state. 10000. This is initial state. What is the second state? What is the second state? After first clock. This is the first clock. Don't say, sir, this is first clock. No, this is your first clock. This is your first clock. This is very, very important thing. Many students are doing wrong here. Okay. So your first clock is this one. So you are going to start from here. After first clock, you will get 11000. You will get 11000. Then after second clock, after this is second clock, what you will get? After second clock, sir, this is 11100. Then what is after third clock? Then after third clock, what you are getting? This is, sir, 11100. Then 1. So after third clock, what you will get? This one is goes to 0. So 1110, and this is 0. What you will get? 11100. So after fourth clock, 11100. Then after fifth clock, this is after, sorry, first clock, this is second clock, this is after third clock. This is after third clock. You are getting 11100. Then after fourth clock, sir, after fourth clock, 11101. So after fourth clock, you are getting here, this is 11101. So sir, this is the output. No. Now again one more, after one more clock, again this same value is going to be repeated, 11101. Okay, this is your fourth clock, and this is your fifth clock. This is your fifth clock. I will explain. If you are not comfortable, wait for that. Okay, now, so one more example I will take. So here just I have assumed here 29.7 volt. So this we have assumed here, first V in, sir, 29.7 volt. So what I have assumed here, 29.7, and here you can write this is the AND conversion. This is the AND conversion. This is AND conversion. Now, sir, if suppose I am going to change the input 29.1 volt, suppose, for example. So if I want to change this V in 29.1 volt, okay, there are slightly difference. They are very slightly different. Now suppose, sir, if V in is equal to 29.1 volt, then what will happen? So again, you have to start. Don't write this 0. Okay, generally this, because of this, student will write, sir, after this first clock, second clock, third clock, fourth clock, fifth clock. No, in last, after this, again you have to check your input is more than that or less than that. your input is more than that or less than that. Okay, so now sorry, here suppose I am going to change something. Suppose this is 16. Okay, input I will change. First 16, then 24, then 28, then 30. Okay, then 29. Okay, now here suppose I am going to change. Suppose this is 28.7. If suppose this is a 28.7 volt. If this is 28.7 volt, then sir what will happen? Then what will happen? Okay, so in this case again you will first start from where, sir, 16 volt. Okay, then after your input is more, so then after you will jump to 8 volt. 8 volt means this is 24 volt. Okay, again your input is more, and after 24 you will jump to the 30 volt. Then again your input is less, so then you will jump to the after 24 you will jump to the 28 volt. Then again your input is more, then you will jump to the 30 volt. Okay, clear this point? Now again your input is less, then you will jump to the 29. This is 29 volt, and now your input is 28.7. Your input is here, this is 28.7. so now my question is, where you will stop? Where you will stop? So now I will start my gadi. So now I will start my vehicle from here. This is start conversion. This is start conversion. What is your initial state? Not initial. This is not after first clock. Sir, 1 0 0 0 0. Okay. Then after first clock. This is your first clock. Sir, after first clock. What I will get? So initially, sir, this is 1 0 0 0 0. Okay. So you will check after this. This is first clock. So you are if increasing, so this bit is fixed to 1. This bit is fixed to 1. So every bit you have to fix. So after this, if you are moving upward, so this bit is fixed to 1. Now again, what will be, sir, here? 24 means 1 1 0 0 0. Then again you are increasing. It means, sir, this bit is again fixed to 1. Every bit you have to check that bit will be 0 or 1. So now in the next clock, again, sir, this is 1 1 1 0 0. Then again you are increasing. Sir, it means this bit is fixed to 1. Already the first two are already fixed, sir. Now again this is fixed to 1. Now again you are increasing here. This is 30 volt. So 30 volt you can write, sir, 1 1 1 1 0. This is 30 volt. But you are decreasing. It means, sir, this bit will change to 0. This bit will change to 0. So 4 bit is fixed. So every bit you want to check, sir, this bit will fix to 1 or this will change. Suppose if you are moving downward, so this will be 0. So if in the next state, if you are increasing, it means this will be 1. And if you are decreasing, then it will be 0. Are you getting this point? So if you are decreasing here this is increasing. So if you are decreasing here, means this bit will change 1 to 0. Now this is 29 volt. Sir, 29 volt means, sir, this is 1 1 1 0 1. But again, this last bit you have to check. Sir, this is 1 1 1 0 1. Sir, what will be the last bit? Last bit will be 1 or last bit will be 0? Sometimes student will do last bit always 1, and that's why they will be wrong. Then you have not stopped at 29. Now again you will check your input voltage is more than this or less than this. Input voltage is less than this. It means, again you will go down. So you will go down to 28 volt. So you will go down to here 28 volt. So here you are decreasing. It means this bit will change to 0. So your output will be 1 1 1 0 0. Your output will be 1 1 1 0 0. This will be the output. So here, if I will write this complete conversion, so how you can write? You have started from here. Your next state is, sir, 1 1 0 0 0. Okay, what is the next state? This is after second clock. This is your second clock. After second clock, sir, 1 1 1 0 0. Then after third clock, what you will get after third clock, sir? 1 1. This is 1 1 1, and now this is going to be 0. This is 0 0 1 1 1 0 0. Okay, now in the next fifth clock, now in the fourth clock, after this is first clock, second clock, third clock, fourth clock, fifth clock. Okay, so now this is 1 1 1 1 0. Okay, this is wrong. 1 1 1 1 0. Okay, now in the fourth clock, sir, this data is 1 1 1 0 1. And now in the fifth clock, In the fifth clock, sir, this data is a 11100. This is the answer, 11100. So first you have to write in this way. And this is not a after first clock, this is after first clock, this is after second clock, this is after third clock, this is after fourth clock, and this is after fifth clock. This is after fifth clock, this is after fifth clock, this is after fifth clock. Okay, so after first clock, this initial you are getting 11000. Then after second clock you are getting 11100. After third clock, this is 11100. Okay, we did wrong. 111 here already. Previously I was written corrected. 11100. Then after fourth clock, okay, no. Okay, you have to write this value. Na, here you have to write this value. Okay, don't write this value. 11110. Okay, so this value you have to write. Okay, after that sometime this will change. So after first clock this, after second clock this, after third clock this, after fourth clock this, and after fifth clock this one. Okay, so if I will ask you what is a final binary value 11100 and what is corresponding voltage, so this is 16 plus 8, 24, 24 plus 2, this is 28 volt. This is 28. This is very important thing. Many students can be wrong here. Many students can be wrong here, especially in this step. Sometimes some student can write this answer, but this will be wrong. So now how you can remember in GATE exam? Okay, so in GATE exam you don't have to solve like this. You don't have to solve like this. If examiners are interested in binary value and corresponding voltage, so one thing if you remember, always here your output voltage will be stopped at bottom. So here one thing if you remember, sir, output voltage V output will be always less than V in. This thing you remember. In counter type we have studied, always your output will be stopped at upper portion or upper states. Okay, upper states of the input voltage, but here always lower state. This is very important, always lower state. So here always if input is 28.7, so your output will stop at lower portion. So output cannot be more than input voltage. Here this is first important point. Output voltage, this output voltage cannot be more than input voltage. Only if you remember this thing, always you will be correct here. So now you don't have to solve like this in GATE exam. Suppose if number of bit is provided, step size is provided, so easily you can find out where this will be stopped. So just you can say, sir, what will be the maximum possible error? So definitely step size. So one step can be less, this can be stopped, this can be stopped. So if this is the situation level 0 and level 1, so if suppose for example your input voltage will be this, so this will be stopped here, this will be stopped at a bottom level. Always here possible error is del, again del. So here you can write QE max, maximum quantization error, again it can be possible del. But if you are considering plus del or minus del in your counter type, so here this will be opposite of that. If you are considering in previous case plus del, so here this is minus del, or if you are considering previous minus del, you can write here plus del. Examiner are not interested in plus del or minus del, they are interested in the value only. Clear this point? So one thing you remember, always here output will be stopped at a lower level. So already here this was stopped at lower level, but here many students will stop at 29 because this is 28.7. So what they will assume, 28.7 is near to 29. So many students will stop this value at 29, and then answer will be wrong. Clear this thing? Now the second important thing, error is here. Sir, what is the conversion time? So here conversion time TC. So TC is fixed always, and TC is not depending on. So one thing is TC is equal to, can I write N into T clock? Can I write N into T clock? Here this TC is not going to depend on the input voltage. Input voltage can be anything. So in first clock you will check this every bit 1, 2, 3, 4, 5. So exactly what we are doing here, in every bit we are going to check every digit is 1 or 0. Okay, so in first clock we are going to check this will be 1 or 0. In next clock we are going to check this will be 1 or 0. In next clock we are going to check this is 1 or 0. In next clock we are going to check this is 1 or 0. And in the last clock we are going to check this is 1 or 0. So in every clock we are going to check every data. So in the first clock, okay, we are going to check this will be 1 or 0. And in second clock we are going to check second and third and fourth and 5. Okay, so every bit we are going to check in every clock. Clear this point? So here for if n is equal to 5 bit, so only 5 clock is required. So one thing you remember here conversion time, here you can write, sir, conversion time is independent of input voltage. Input voltage can be anything. In this circuit 5 clock is required. So sometime here examiner can ask you the question, suppose for 28.7, suppose 5 millisecond conversion time is okay required, then suppose if input is changed, then how much conversion time will be required? Same conversion time. Okay, so input will not decide how much conversion time will be required. Clear this one? Now I am going to take one more question from here. I hope this thing is clear to all of you. Just confirm me. Okay, just confirm me. This thing is clear to all of you or not? Just confirm me. Very, very important thing I am going to discuss. In GATE exam, many students generally getting wrong answer in ADC and DAC. And after that, they will blame to IIT. Okay, they are providing wrong answer. No, at least you have to study the exact circuit where your output is going to be stopped. So you should know this thing. In counter type, you are going to stop at upper portion in a standard circuit. Okay, we can design where we can stop at lower circuit, but in a standard circuit, always you have to stop at upper portion. Here, always you have to stop at lower portion. Clear the thing? So one question I am going to consider from previous year. I can take one question. Okay, now I hope this thing is clear to you. So here two things you should remember. So what is maximum condensation error? That is a del again, and always your output will be stop at the lower your step, and conversion time is independent of the input voltage. How much conversion time? N into T clock. Now if I will ask you from previous counter time and successive approximation, which circuit is better? This circuit is better. So first method in real life generally we don't use, especially for more bit. So if your bit is more than 5, we generally go with successive approximation. Okay, but in real life generally again we don't use successive approximation because we need a quantization error del by 2. So that's why in real life again we don't use successive approximation. Clear this point? Now one more question I am going to take from here. Clear this? Now one more question I am going to take from here. Okay, so generally from counter type, generally they will not ask you the question. Okay, from successive approximation, this is very important topic. Most of the question generally asked from the successive approximation, and in the last states generally students are getting wrong answer. Okay, now suppose if in GATE exam same question will be asked by the examiner. Suppose if a same question is asked by the examiner. Suppose 28.7 volt. Okay, and now the step size is 1 volt. This is Vin, and step size del is 1 volt. So where this will stop? Step size is 1 volt. So for 28.7, you have two steps, 29 volt and 28 volt. And already I tell you, always you have to stop at lower level. So your result will be, your output V0 will be 28 volt. And now you can write corresponding binary value. If this step size is 1 and here this is n is equal to 5 beta. So in 5 beta, if step size is 1, how you can write to 28? How you can write to 28? Sir, 16, this is 16 plus 8, 24, and this is 28. This is the answer. So you don't have to write this thing. If you know this thing, always output will stop at lower level. Now if the same question, suppose sir, if step size is here 2 volt, so step size is if here 2 volt, then first for this both the step you have to find out, or all the step you have to draw. Suppose for example I am assuming, sir, this is 4 bit. Okay, 4 bit, and suppose step size is here del is 2. Okay, So if del is 2 and this is, so you can write, so 2 raised to power 4 into 2, 2 raised to power means 16 into 2, so this is 32 volt. So this is V reference. Sir, V reference is 32 volt. So V reference by 2 will be 16. So you can draw in this way, sir. This is 16. Sir, this is 16 plus this is 8. This is 16. So 16 plus 0. This is 16. This is 0 volt. So this will be 16. 16 plus 8. Sir, this is 24. So you will get here, sir. This is 4. So 28 plus 4. Sir, this is 28. Like this. And 28 plus again this is 2. Sir, this is so how many bit? This 16 means 1000. This is 4 bit, no? This is 4 bit. This is 4 bit and step size is 2. Okay, so this is, sir, 100 means 16. Okay, and sir, 1100 means 24. 1110 means 28, and 1111 means this is, sir, 30. This is 30. Okay, this is the last step size. So your step size, so this you will get. Now you can see where is your input. Suppose our input is 28.7. So here you will get 28.7. So where this will be stopped? Where this will be stopped? Definitely you have two levels, so 30 or 28. So you will stop at 28. You will stop at 28. And 28 will be written by here 1110. So your output voltage will be 1110. Like this. Directly you can write the answer. But if examiner are interested in this conversion, complete conversion, okay, then you have to draw like this. But if examiner are interested in complete conversion, so they will provide you 4 options. So just you have to take one answer. No worry, just I am going to take one question from here. So like this you can handle. So very important point. If you remember, output voltage will be the lower voltage. Definitely any question you can handle. So only this basic thing you should know. I hope this thing is clear to all of you. Now one more question I am going to take from the previous year. Okay, definitely there are so many chances examiner can ask question from the successive approximation. Clear this point? Okay, now one more question I am going to take. They have given 4-bit successive approximation ADC. Just note down here, this is a 4-bit ADC. 4-bit ADC. Okay, 4-bit ADC is given, and this is successive approximation, and full scale voltage is 15 volt, and this is successive approximation. Successive approximation we write sometime SAR. Okay, remember sometime examiner can use SAR, successive approximation register. Okay, they can write in this way. So SAR, successive approximation. Okay, so sometime they can write SAR. So don't get confused. 4-bit ADC, this is SAR is given. Here FSP is given 15 volt. Here full scale voltage 15 volt is given. So if FSP is this 4-bit, it means step size is 1 volt. Can I write step size? So my first target is step size is 1 volt. Okay. Now what they have provided, if input voltage is 8.15. So if input voltage is equal to 8.15 volt, what will be the conversion? So they have provided you the 4 options. They have provided the 4 options. But what is the final answer? Final answer easily you can find out. Yes, sir, easily we can find out. How you can find out? So what is step size 1 volt? If step size is 1 volt, it means 8.15, this is 9 volt and this is 8 volt. And already I tell you, always at lower state, this will be stop. So your output will be 8 volt. And 8 volt will be written by, if this is 4 bit and 4 bit FSC, it means FSC 1111 means 15 volt. So sir, what do you mean by 8 volt? 8 volt means this is nothing but, sir, 1000. This is 8 volt. This will be the answer. So your last state will be 1000. So if you can check all the 4 options, where you are going to stop, okay, so that you will be stop at 1000. I am providing you 4 options. You have to give me the answer. Here. I hope this thing is clear to all of you. Now here 4 options I am going to provide you, and then, sir, what conversion we will get? This thing you have to tell me. So I am writing here 4 options. First option, okay, option number A. In first option they have provided 1000. This is start conversion. Okay, this is start conversion. 1000. This is number 1. Okay, after 1000, then after 100, this is 1100. Now then after 1100, now the next state is 1010, and now this next state is after 1010. Okay, this is 1001. This is 1001, and after the next state is after 1001, the next state is 1000, and this is AND conversion, and this is AND. So you can see how many state 1, 2, 3, 4, 5. But 4-bit 4 clock is required. It means this is initial. This is first clock. This is second clock. This is third clock, and this is fourth clock. Okay, this is fourth clock. After fourth clock, you remember if 4 clock, so you have to write 5 value 1, 2, 3, 4, 5. This is the important thing. Many students will write only 4 value, and they can be wrong. Okay, and they can be wrong, This is option A. Now the second option. In second option, this is start conversion. This is start. Again, this is number 1. This is number 2. This is number 3. This is number 4, and this is number 5. And this is your end. Okay, just I am writing where we are getting 1000. That option only I am going to write. Okay, in second option we are getting last 000. That is wrong. In third option we are getting 1111. Again, that is wrong. And in the last option, in here I am going to write. We are going to start from 1000, and the second state is 0100. This is 0100, and now the next state is given here 0010. Sir, this is 0010. This cannot be possible. Okay, but we have to check. And then 0001, and then 1000. How it can be possible? So always you have to check one bit. This is a fixed 1. So always this will be 11111. It cannot be modified. Every bit we are going to check. So here easily you can take the answer. Take the answer. Okay, suppose if I want to draw this, so you are going to start from 8. So you are going to start from 8 volt. You will check the input voltage is more than this or less than this. So more than this. So this is nothing but 1000. So definitely you have to go up. How much go up? If this is 8 volt, so 4 volt you have to go up. It means this is nothing but 1100. Okay, now this bit is fixed. If you are moving up, so this bit you can say fixed. This is 1. This is fixed, or you can write here. Here I can write this is fixed. This is 1100. It means this bit is fixed. This is 1. Okay, so now how much you have to move this 4 volt? So 8 plus 4 will be 12 volt. So now you can check your input is less than this. Okay, less than this. How much less you have to down here? This is 4. So again half. So how much you have to down? 2 volt. 2 volt. 2 volt means you have to reach to here 10 volts. So if you are doing down here, it means, sir, this value will change to 0. This value will change to 0. It means, sir, what you will get here? This is 10, and you will write, sir, here 10. This will change to 0, and this third bit you have to do 1, and you have to again check. Now again this is 10 volt. Again your input is less than this. So less than this, again you will change to, this is 2. So 1 volt you will down. 1 volt you will down. So you will reach to here 9 volt. You will reach to here 9 volt. Okay. You will reach to here 9 volt. You will reach to here 9 volt. Okay. So now what will be this bit? You are going down. It means this will become 0. So 9 means, sir, 1001. Now again you will check the last state. Again when you have reached to the step size, this is step size. When you reach to the step size, then again in the last state you have to check that last bit will be 1 or 0. So every bit you have to check. This bit will be 1 or 1. Sir, this bit will be 1. So this bit will be 1 or 1. So this will be 0 because you are going down. So this bit will be 1 or 0. You are going down. That's why this is 0. So last bit will be 1 or 0. So again in last you have to check your input is more than this or less than this. Sir, our input is less than this. So again this will goes to down. So this will goes down to 8 volt. 8 volt, and 8 volt means, sir, 1000. It means, sir, this bit we have to change to 0. Okay, so this step you are getting, but how you will write this? So you can see the answer. So you have to start from 1000. You have to start from 1000. You will write this blue color here. This, sir, 1100. Then 1100. Initial 1000. So first you will write here, sir, 1000. This is start. Okay, then after first clock, this is after first clock, you will get, sir, 1100. Then after second clock, what you will get? Then what you will write? Sir, I will write 1000 or I will write 1010. You can see here. So you have to write this blue color 1010. This is 1010. Then sir, in the after third clock. Then after third clock, here this is 1001. Again you can see here 1001. What you will write, sir? This is 1001. Then after fourth clock. Then after fourth clock, sir, what I will get? Then after fourth clock, again you can see here, sir, 1000. So this last will be after fourth clock. So you will get here 1000, and here you will get end. Here you will get end, and here you can write, sir, this is start. This is start. Okay, so how many clock is required? So here this is 4 clock is required. Here this is 4 clock is required. 4 clock is required. Okay, so total 4 clock is required. Okay, sometimes somebody can write after first clock this will get, after second clock, after third, after fourth. You can also write after first, second, third, fourth, and this will be automatically changed to this one. Okay, by using the circuit. So sometime this can be first clock, second, third, fourth, but always clock will be n number of bits, so n clock will be required. But how you will get this states, this is very important. Now I hope this thing is clear to all of you. Okay, how you can write this state. If you know the step size, how you can directly write the final last state. Okay, and corresponding voltage last state you can write, and error you can also write. How much error you are getting here? Sir, our input is 8.15, but we are going to stop at 8 volt. It means here error, in this situation your error is 0.15 volt. At maximum possible error possible in successive approximation is, that is the del, that is the step size del, and output will be always stop at the bottom portion. Okay, so this thing should be remembered to you. Okay, I hope now this thing is clear to all of you. Okay, so this thing is clear, so please just confirm me. Okay, if I will provide you the same question in GATE exam, and if I will stop you at this position, if I will write in this way, so many students will take this answer. But this is totally wrong. Clear this thing? Okay, now come to the successive approximation. So please nexus who are attending the class, just confirm me. Now can you handle this question? Or not? Please tell me. Okay, now the third one is the flash type. Okay, now the next I am going to take third one is the flash type ADC, and that is very simple. Third one is the flash type ADC. Okay, third one is the flash type ADC. Okay, now the third one is the flash type ADC, and this is very easier. So generally they will target question either from flash type or your successive approximation. This is your flash type ADC. Okay, so in flash type ADC, exactly what we have to do. So here we have to use priority encoder. Okay, priority encoder. So priority encoder, suppose I am going to use here 4-bit encoder size, your decoder size n cross 2 store n, here 2 store n cross n. Suppose I am going to use here 4-bit. This is 1, 2, this is 3, and this is 4. Suppose 4-bit. Suppose I am going to use 4-bit. Okay, now this number, okay, this is 4-bit. This 4, suppose I am going to write it here in this way. Okay, now suppose this is first, second, this is 4-bit. I can write, sir, this is I0, I1, I2, and I3. So in priority encoder, if I3 is 1, your output will be 1, 1. Okay, if I am writing this is D1, D0, so if I3 is 1, this is 1, 1. So if I3 is 1, if I3 is not 1, 0, then if I2 is 1, then output is 2, means 1, 0. If both are 0, 0, then we will check I1. If this is 1, output will be 0, 1. If all these 3 are 0, 0, then 100% output will be 0, 0. So this I0 will be always 1 here. I0 will be always 1 here, and here what we have to do, this I3 we have to connect with one comparator. Okay, this we have to connect with one comparator. This is comparator. Okay, so I3, I2 and I1. So for this is, you can say this is nothing but output is 2 bit. So this is a, you can say 2 bit. This is a 2 bit ADC. So this is your 2 bit ADC. Okay, this is 2 bit analog to digital converter. 2 bit analog to digital converter. Okay, 2 bit analog to digital converter. And how we can write? Here suppose we are going to assume V reference. So here one resistor and this is connected here. One resistor, this is connected here. Here one resistor, this is connected here, and one resistor, this is ground. So one thing you remember, for 2 bit ADC we have to use encoder 2 raised to power n cross 2. So the encoder size is 2 raised to power 2 cross 2 means 4 cross 2. This is 4 cross 2 means 2 raised to power n cross 2. This is 2 raised to power n cross 2. Okay, so here you can write this is 4 cross 2. So this size is a 4 cross 2. You can write 2 raised to power n cross n. You can write 2 raised to power n cross n. Okay, if you want, you can note down this. Now here exactly what we are doing. You can see here, sir, this is minus, sir, this is minus, this is minus. Now here this is 1 plus point and 1 plus point, 1 plus point. Here in plus point, here in plus point, and here in plus point. What we have to connect? So in plus point we have to connect your input voltage. Your input voltage. This is V in. This is V in. So here exactly what we want to do. Suppose this resistor is R, this resistor is R, this resistor is R, this resistor is R. So here exactly what we are doing. One more thing, remember, all these three are the comparator. So this and this are the comparator. This is a comparator. This is a comparator. So comparator, how comparator will work? If positive is more, output is 1. If negative is more, output is 0. So in comparator, if positive voltage is more than 0, means this 0 negative voltage. If positive voltage is more than negative voltage, output is 1. If positive voltage is less than negative voltage, output is 0. So here exactly what we are doing. You can see, sir, this is V reference. So here if I will find out voltage, so V reference, this is R. If you will connect this in series, sir, V reference into R divided by this 4R. So here you will get voltage V reference by 4. Here you will get voltage, sir, V reference by 2. Here you will get voltage, sir, V reference into 3R divided by 4R. It means into 3 by 4. Okay, so if your input voltage will be more than 3 by 4 V reference, okay, 3 by 4 V reference, okay, then this will be 1. If your input voltage will be in between these two, so this will be 1. If your input voltage will be in between these two, so this will be 1. If your input voltage will be less than this, so output will be 0, 0. So what I can write here, if your V in, can I write here, if V in voltage is more than this, if your input voltage is more than 3 by 4 V reference for this circuit, and what you can write for n bit, V reference by this is 4, this is 2 raised to power n, this 2 raised to power n, to n minus 1, this is 2 raised to power n minus 2. In this way you can write. Okay, sorry, this is V reference into 3R divided by 4R. Okay, so like this you can find out. So every voltage we are going to divide. So V reference you have to divide in 4 part. So if you have V reference and the number of bit is 2, so 2 raised to power n, it means sir, V reference you have to divide by 4. So first step is V reference by 4, second step is V reference by 2, third step is 3 by 4 V reference is 0.75. So this value is sir 0.25 V reference. Sir, this value is 0.5 V reference. Sir, this value is 0.75 V reference. So this V reference you are going to divide into 2 parts. Okay, you are going to divide into 2 parts. Suppose if this is a 3 bit, so this will be divided into 8 parts. Okay, so what we are doing exactly here, V reference, you are going to all the you can say step size voltage you are going to find out. What is a step size? So step size is nothing but V reference by 2 raised to power n. Here n is 2. It means V reference by 4. What is the first step? First step, if this is 0 volt, Your first step is V reference by 4. Sir, this is V reference by 4. Sir, what is the second step? Sir, V reference by 4 into 2 or V reference by 4 plus V reference by 4. This is V reference by 2. Sir, what is the third step? Sir, this is V reference by 2 plus V reference by 4, 3 by 2 V reference into 3 by 2, and then this is V reference. So what we are doing exactly, V reference, we are going to divide here in every step size voltage, and every step size voltage is available. In previous design, what you are doing exactly, every step size voltage you are creating, but here all the step size voltage is already available. So this voltage is available, this voltage is available, and this voltage is available. All these three voltage and 0. If this nothing you will get, then output will be 0 0. So all these three voltage we have created here. Already this voltage is available here, this voltage is available here, and this voltage is available here. Now just you are going to check your input, where input will lie, how many conditions can be possible. So can I write here, if first case your V in is more than or is equal to, this is 3 by 4 V reference, 3 by 4 V reference. Okay, now the second case, this is first condition. Now the second condition, if V in, you can write, sir, this V in is less than 3 by 4 V reference. Can I write? If this is less than 3 by 4 V reference, but this is greater than or is equal to, we can write this value V reference by 2. This is V reference by 2. And third you can write, so one thing you can remember, if this value and this value are equal, output is 1. Sometimes student get confused. So if both are equal, then what will happen? If both are equal, output will be 1. Okay, now in third case, sir, if V reference is greater than or is equal to V reference by 4 but less than V reference by 2. This is third case. And now the fourth case, sir, if V in is less than, sir, V reference by 4. 4 case can be possible. If V in less than this, means between this two 0 volt, now are in between this two or more than this, then what will be happen in the circuit? I hope this thing is clear to you now. So here what we are doing, all the step size voltage is already available, and just you are comparing where your input voltage will lie. If your input voltage will lie here, so first you will check to this one. If your input voltage is lie here, then your output D1 and D0, then D1 and D0 will be 1 1. And if this is not satisfied, then you will check to this, then your D1 D0 will be 1 0. And again, if this will not satisfy, so you will check here, this will be output 0 1. And here if input will lie less than of this voltage, so this will be already 1, output will be 0 0. So this will be 0 0. Okay, so like this you can handle, So here sometime examiner can be interested, some 2-3 things should be clear to you. Sir, how many number of comparator used? The number of comparator used, you can write, sir, 2 raised to power n minus 1. So for n bit, if n is equal to 4, so 2 raised to power 4, that is 16 minus 1, 15 comparator is required. Okay, sir. Now the second, number of resistance. How many resistance you are using here? This is 2 raised to power n. This is 2 raised to power n. You can see, sir, 1, 2, 3, 4. Okay, and third important thing you remember, this is a priority encoder. Okay, this is a priority encoder. So if this is 1, so it will not check to this. Output will be 1 1. If this is 0, then it will check to I2. And if this is 0, then it will check to I1. If this is 0, then it will check to I0. Clear this one? So this is called priority encoder. Okay, so this basic thing should be very clear to you. Now the important thing, sir, here, what is the maximum possible quantization error? So QE max, again here it can be del. Suppose if your input just below to 3 by 4 V reference, then output voltage you will get corresponding to this. Output voltage you will get corresponding to this. So again you will get here error is step size, that is a del. Now here one more important thing, in this question I have considered R. But in real GATE exam, examiner can use this R by 2, this R by 2, this R. So this R can be modified. So here the advantage, what is the important thing? Here every step is same, but here if you want to create random step, so right now what we are using here, every step size is same. Sir, this is del, this is del, this is del, this is del. But in this case, this step size you can modify, and you can do, sir, this is del 1, this is del 2, this is del 3, this is del 4. This is very, very important. How you can create? Just you can control the value of this R. So if you will change here value, this R1, this R2, this R3 and this R4. So by using this R1, R2, R3 value, you can control all the step size. This is the most advantage of this flash type ADC. Are you getting this point? So examiner can ask you this question. If a different step size is required, then what we can do? You can use flash type ADC. This is very, very important thing. Okay, this is very, very important thing. I hope this thing is clear to all of you. Clear this point? So very few people know this thing, but already 3 times in GATE exam they have asked question from here, and they have provided different value of resistance. This is basic network theory. If they will provide you V reference, different R value, you can find voltage here, you can find voltage here, you can find voltage here. Then according to input voltage, you will get corresponding binary. And if you will get, suppose here binary 1 0, and you know the V reference and you know the step size, so what will be the corresponding voltage for this? Easily we can say, easily we can find out. Okay, so I hope now we can handle. So this thing should be clear to you. So what is the maximum possible error is here? That is again step size. Now the important thing is, sir, what is conversion time? So here conversion time is, so when you will provide input, you will get output. Conversion time is ideally 0 seconds. So you can write here only propagation delay of this. So can I write here, no clock is required. Here no clock is required. So for this conversion, no clock is required. Sometime student can use 1 clock, but it is not a sequential circuit. Always your answer should be no clock is required. So here conversion time is independent of T clock. So this is very, very important thing. So here conversion time is independent of the clock time period, because there are no clock is required. So when you will enable this circuit, suppose I am saying, sir, here one enable. So suppose if you have provided input, and when you will enable the circuit, you will get output. Definitely this propagation delay will be added. Right now we are assuming all the propagation delay is 0. So when you will provide enable signal, you will get output here immediately. So here no conversion time. Here, sir, if number of bit is more, if suppose this is 3 bit, 4 bit, 5 bit, then again same answer. So again TC is again independent of, you can write this thing, this conversion time is independent of the input voltage. This conversion time is independent of the clock time period. Conversion time is independent of the number of bits. So here conversion time is, because answer is 0 second. If answer is 0 second, it means conversion time is not going to depend on any parameter. Yes, one parameter, this delay and this delay. Clear this point? I hope this thing is clear to all of you. So please just confirm me. I hope this thing is clear to you. Okay, so if anybody have any doubt in this, just tell me. Can I take one question from here? Okay, so one question I am going to take from here. Okay, now. So can we take one question from here? Yes, okay. So one question I am going to take from here. Okay, now. And this is very, very good question. Okay, just note down. Everyone note down. So which category of question can be asked? Okay, from here. So just note down. So flash type, 2 things should be very clear. Number of comparator, sometimes they can ask you. Okay, number of resistance, nobody will ask you this thing. What is conversion time, and what is here? Quantization error maximum possible quantization error. Okay, but if anybody will ask you, sir, where we will use flash type? So in general, flash type will be used where different step size, where your quantization level is different. All the quantization level step size is different. In that place exactly we can use this flash type. Okay, now, so just note down one problem from this flash type. Just note down one problem from this flash type. So here, just note down. So here, one digital circuit is given. This one block is given. This is a digital circuit. This is a digital circuit. This is a digital circuit. Okay, and here, three input is given. This is 1, this is 2, this is 3. Okay, now, and 2 output is given. Okay, sometime this I0 they will not provide. Sometime. Okay, now here 3 comparator is connected. This is first comparator, this is second comparator, and this is third comparator. 3 comparator are connected here. Okay, and now here this is plus minus, this is plus minus, and this is plus minus. Okay, and this value they have provided. This is x0, this is x1, and this is x2. Okay, anything they can write. And output they have provided. This is b1 and this is b0. Okay, this is b1 and this is b0. And now all this positive is connected with the input voltage. All this positive is connected with input voltage, and input voltage is a V in. Input voltage, and they have written this is V in. And all the negative, here I can write, sir, this is negative, and this is negative. Here one resistor, here one resistor, here one resistor, and this is ground. Here one resistor, and here this is V reference. And here this V reference is given 3 volt. This voltage directly they have provided here, and resistance value is different. First resistor is 100 ohm. Now second resistor is here 200. Third one is 200. So here all the resistance value is different. This is 200. This is 200, and again this is 100. So first and last one is 100, and middle both are 200. Okay, now you can write. Okay, now I am going to read out the question. A 8-bit unipolar successive, sorry. Okay, now the question is different. A 2-bit flash type analog to digital converter is given below. The input voltage range is 0 to 3 volt. So here input voltage range is V in. V in is less than or equal to 3 volt or greater than or equal to 0 volt. So V in can be between 0 to 3 volt. Okay. The expression for the function B0 and B1. So expression for the B0 you have to find out. So B0 function we have to find out in terms of x2, x1, x0. 4 options I am going to provide you. First option is given, sir, x0. Okay, first option I am going to provide you. This is x2 XOR x1. X2 XOR x1 is first option. Now the second option is given here. This is x0 bar, and this is x2 XOR x1 whole bar. Okay, this is second option. And third option is given here. Sir, this is x0, this is x0, and here given in first option this was also bar. Okay, in third option this is, sir, x2 XOR x1. Okay, now, and in the fourth option is given this is x0 bar, and this is x2 XOR x1. This thing is given. Anybody can solve this. I am waiting for your answer. Okay, I am waiting for your answer. This is, you can say, basic network analysis you have to apply here, and digital. Okay, first you have to find out all the points voltage, and then you have to find out a function. Okay, so is there first thing, sir, this voltage is required or not? Sometimes we don't have to calculate this voltage because the voltage calculation is not required. The voltage calculation is not required many times. Many times this voltage calculation is not required. This is very best and very good question. Okay, so all the topic I am considering which kind of question examiner can target. Okay, so anybody can tell me answer. I am waiting for your answer. I am waiting for your answer. Okay, you should try. This is very easier question. This is very, very easier question. So here just I want to give you one thing. You don't have to calculate here voltage. This voltage is not required because you have to write B1 and B0 in terms of this 3. Okay, so you don't have to calculate here input voltage. Input voltage is not required. So here you can see what is input. Sir, input is x2, x1, x0. You can draw the truth table directly. And sir, what is output? B1 and B0. What you can say? Sir, if x2 is 1. So if this x2 will be 1, when x2 will be 1, your this input voltage will be more than this volt. Suppose if I can say this volt, and this volt. Suppose this volt is V1, this voltage V2 and this voltage V3. So if your input voltage is more than V2, V3, then definitely it will be more than V2, definitely it will be more than V1. So here in encoder, if this is 1, so this is understood, x1 will be 1 and x0 will be 1, that is understood. So if x2 is 1, it will be understood, x1 100% it will be 1 and x0 100% this will be 1. Suppose for example, if this is 3 volt, suppose your input voltage 2.5 volt, suppose for example. So if 2.5 volt is more than V3, so definitely more than V2 and definitely more than V1. So if x2 will be 1, so 100% x1 or x0 will be again 1 1, because if this is 1 means this input voltage will be more than this, and already this is less, this is less. So in here encoder, if your this you can say MSB point, if I am saying this MSB, this LSB, if MSB is 1, so remaining all definitely that will be again 1. So if this is 100%, this will be 1 and 1. So in this case, what will be V1 B0? Sir, V1 B0 will be 1 1. Now the second case, sir, if x2 is 0, okay, but if this x1 is 1, so if x1 is 100%, x0 will be 1. In this case, sir, B1 B0 will be 1 0. Sir, if x2 is 0, sir, if x1 is 0, then if x0 is 1, in this case, sir, this is 0 1. And sir, if all these three are 0 0 0, if all these three are 0 0 0, so sometime examiner have to return here 1, and this is actually 4 input and 2 output. Sometime examiner will not write. It means if all these three are 0 0 0, it means output will be 0 0. So this will be 0 0. But now this truth table is not completed, not completed. So here, if you want to complete the truth table, suppose for example, here this is 0, this is 1, this is 3 and this is 7. Here 4 value is not present. So how you can find out this value? How you can find out this value? So you can see here, now the important thing, now the digital, here digital basic concept is very required. Sir, here for 0 this is 0 0, for 0 0 1 this is 0 1, for 0 1 1 this is 1 0, for 1 1 this is 1 1. So suppose for example, from here if you want output you can find out, but if you want to complete the truth table, suppose this is x2, sir, this is x1, this is x0. Suppose if you want to complete the truth table, sir, this is b1 and this is b0. First I am going to write, sir, 0 0 0. Already this is available, okay, and the output is 0 0. Now sir, 0 0 1, yes, available. Sir, 0 0 1 and the output is 0 1. Okay, sir, 0 1 0 available, no. So if I will write 0 1 0, practically this can be possible. If this is 0, this is 1, this cannot be 0. It means this input cannot be possible. So if this input cannot be possible, so this output will be don't care. You can write output will be don't care. If input will not exist, so corresponding output will be don't care. If output is don't care, means this input you cannot use in the circuit. Now the next, sir, 3 is available, yes. So for 3 output is 1 0, okay. 4 is available, no, because 4 cannot be possible. If this is 1, this 2 cannot be 0. If this is 1, this should be definitely 1. So this input cannot be possible, so output will be don't care. Now the next, sir, 5 is available, no. So 5 again cannot be possible, so your output will be don't care. So 6 cannot be possible, so again this output can be don't care. Yes, 7 is already given, so this output is 1 1. Now you can find out exact minimize function, but you have to check examiner have provided here minimize function or not. So just I have provided both the truth table. This is the complete truth table. So for any kind of circuit in any kind of situation, suppose if you will get 4 input and according to that output, and remaining 4 input if not available, or you can say you cannot use in the circuit, so just you can write corresponding output is don't care. Already I have tell you the meaning of don't care. So now you can find out the function of b1 and b0. So if you want to find out function of b1, so you will get minimize function, but we have to check examiner are asking here minimize or not. So if sir, this is b1, this is 0 0 0 1 1 0 1 1, this is 0 1, and here this is nothing but x2 x1 x0. So this is x2, this is x1, this is x0. So 0 0 x1, so this is 0 0, this is x1, 0 0 x1, x x x1, x x x1. Okay, so from here, if you want to write b1, if you want to write, sir, b1 function, so if you want to write b1, what you will get b1 exactly? So you can make a group here, this 2 1, so can I create group for this? So I can write here minimize function of b1 is, so minimize function of b1 is nothing but only x1. So minimize function of B1 is x1, but they have asked here B0. They can also ask B1. They can also ask B1, and this question is also asked in GATE exam. In one time they have also asked what is the B1? What is the B1? Now the second answer. Okay, what is the B0? This is a minimize function. This is a minimize function. Sir, what is the B0? They have asked B0. So now you can check from here. Now you can find out from here. This is your B0. This is your B0, and here this is x2, x1, x0, and this is 0, 0, 0, 1, 1, 0, and 1, 1, and this is 0, 1. So here B0 is 0, 1, x0. Sir, this is 0, 1. This is don't care 0, and then don't care 1, don't care 1. So what is a minimize function here? If you want minimize function, so sir, minimize function is this one, this group, and this one you can collect from here. So what is a minimize function of B0? So B0 from here you can write, sir, this complete means this is x2, and this x2 plus, from here you can write, sir, this is x1 bar, and this is x0. So this B0 is x2 plus x1 bar x0. This is a minimize form. This is a minimize form. But examiner have not provided you minimize form. Examiner have not provided you minimize form. So how you can write? Yes, directly you can write. If you want to write non-minimize form, suppose, so directly you can write from here, sir, this is B1 and this is 2 times 1. So this you can write min term. You can write, sir, this is x2, x1, x0. Okay, and this 0, 1, 1 means you can write, sir, x2 bar, x1, x0. So if you don't want to write minimize form, so B1 function is nothing but this is B1. Sir, and this is second one, and this is first one. So what will be the B1 from here? This is x1, x0 you can consider common. Then x2 plus x2 bar is 1. So the answer is x1 into x0. This is a non-minimized form. So if you will not use here don't care, so just you can create this group. And this group will be nothing but x1, x0. This is non-minimized form. So here examiner can ask you two category of question. Okay, one is the minimized form, one is the normal form. So either B1 can be x1 or B1 can be x1, x0. Okay, so two answer can be possible, but examiner will provide you only one answer. Now come to the second question. Sir, this is a minimized form. Okay, if you don't want to write this minimized form, directly you can write this one, and directly you can write this one. So what will be the, sir, B0 without minimized form? So this one you can write from here, sir, this is x2 bar. This x2 bar from here, this is x1 bar x0 plus, and this one is nothing but, sir, x2, and from here x1 x0. So which term is common here? Which term is common here? X0 is the common. So you can write here, sir, this B0 is x0 is the common term, and x2 x1 plus x2 bar x1 bar XNOR gate, or you can say XOR bar. So this is x2 x1 XOR whole bar. Can I write? So which is the correct answer for B0? X0 multiply this A is the answer. This A is the answer. This is not minimized form. So directly you can write, either you can write this one and this one. Okay, so examiner can ask you two category of question. Examiner can ask you minimized form, or examiner can ask you non-minimized form. Clear this thing? So two answer can be possible. So till now this question already has been asked, 2 times asked. So according to me, now examiner will be interested in here minimized form. Be ready for the minimized form. This is very, very important question. This is very, very important circuit, and this is very, very important question. Okay, and this category of question in all the branch electrical, electronics, instrumentation, approximate 5 times they have repeated. Approximately 5 times they have repeated. I hope this thing is clear. Okay, yeah, from tomorrow communication I will start. Okay, so this is very, very important thing. So you should be comfortable in this. Please just confirm me this thing is clear or not. Please respond everyone. Okay, please respond everyone. What I am going to teach you right now, please concentrate on that point. Okay, very, very important thing I am going to teach you, where generally students are getting wrong. And if you learn this very basic thing, easily you will get 1 to 2 marks in GATE exam. And that is very, very important. Clear this point? So now tell me if anybody have any doubt here. Okay, so here one important thing, you don't have to calculate, sir, this voltage, this voltage, this voltage. This is not required. This is not required. Now if examiner will ask you, for which voltage this will be 1 1, for which voltage this will be 1 0, for which voltage this will be 0 1, and for which voltage output will be 0 0, you can write. You can find out the 3 volt into 100 divided by 2, 2, 4, 5, 6. 3 volt into 100 divided by 600. This volt. So 3 volt into 300 divided by 600. So this will be 3 by 2. So this will be 1.5. So what will this voltage? 3 into this 2 to 5. 2 2 and 105. So 3 into 500 divided by 600. So this voltage you can write. But examiner will not ask you here to calculate the voltage here. Okay. So this is, you can say, very basic circuit. Okay. Now, so I hope this successive approximation we can handle. Now the last one. So all these three category right now you remember, conversion time should be very much clear to you, and then where it will stop, and then so here I cannot say where it will stop. It will depend on the circuit. It will depend on the circuit. But yes, we can say here if this input is more than this, sorry, if this input is more than this, so output will be 1 1. So in this flash type, exactly I cannot say where it will stop, at upper portion or at lower portion. Everything will depend on the circuit. Okay, so that's why here I am not telling you where it will stop, and examiner will not ask you. Don't worry here. Where it will stop, examiner will not ask you. Okay, so if circuit will be provided, easily we can find out the exact answer from the circuit. Clear this point? But for a flash type and for successive approximation, you remember, for successive approximation, for counter type. For counter type, always at upper portion your counter will stop, and for successive approximation at the bottom side. And error for all the three cases is a quantization error maximum is a del. Okay, conversion time should be also remembered to you. Now the last one. Okay, that is your last one is your dual slope or integrator type ADC. Dual slope or integrator type ADC. That is a dual slope or integrator type ADC. So number 4 is dual slope, or you can also say, sir, integrator type ADC. Okay, this block diagram is some kind of a complicated circuit, and if you have studied this, then only now I can explain you. And if you are attending first time, or if you are studying first time this dual slope, so definitely now this will not be clear to you. Okay, because this is a revision classes, so I cannot go with the block diagram here. So just I want to tell you in GATE exam how you can handle. So here one thing you remember, first in the circuit, by V reference we have to charge the capacitor. Here one op-amp we will use, and there one resistor and capacitor connected. That's why this circuit name is integrator circuit. Now here by V reference we charge the capacitor. Direction is negative, but I am going to draw in this way. Practically the direction was negative, so generally we will charge in this way. So here, and this time is required, suppose T1 time here, N1 clock is required, and here by which voltage this will charge? By V reference. So here the voltage will be V reference. So by V reference this will be charged. Okay, now then by V in we are going to discharge, and by V in we are going to discharge, and this is definitely very basic thing. V reference will be definitely more than V in. V in will be 100% lesser than V reference. So V in will be 100% lesser than V reference. So now capacitor will go discharge. So definitely this time will be always less. So this time we can say this time will require T2, and this time require T1. Here number of clock is required, that is N2, and here discharging. So here when you have which voltage you have applied here? V. Just this triangle you should remember. And for T1 how much time is required? So one complete conversion for n bit, 2 raised to power n. So here this n1 is nothing but 2 raised to power n. This n1 is nothing but 2 raised to power n. Sir, what will be the n2? We have to calculate this n2. Sir, what will be T2? We have to calculate this T2. So what will be this time? So T1 can I write 2 raised to power n clock is required. So 2 raised to power n into T clock. Can I write? So here T1 is equal to, sir, 2 raised to power n into T clock, and sir n1 is equal to 2 raised to power n, and V reference examiner will provide you. Suppose we know the V reference. Sir, what will be the T2? T2 we have to calculate. Sir, what is N2? N2 we have to calculate. Sir, V in will be provided by the examiner. V-in will be provided by the examiner. So here, one relation you should remember only. One relation you should remember only. If you have studied this circuit, then this will be comfortable to you. And if you not studied earlier dual slope, so definitely okay. But if you remember this, maybe in GATE exam you can handle the question. So in T1 is 2 raised to power n clock, and N1 is 2 raised to power n. Okay. Now V reference will be provided by the examiner. V in will also be provided by the examiner. Okay, because V reference and V in they will provide you number of bit, they will provide you, and we have to calculate T2 and N2. So one relation you should remember. How you remember? So you can say, sir, T1 by T2, which is more? Sir, T1 is more. Okay, sir, if T1 by T2, T1 is more, then this relation will be greater than 1. Okay, so you can write in terms of N1 by N2, which is more? Sir, N1 is more. So sir, you can write N1 by N2. Now again you can say, sir, V reference and V in, which is more? Sir, V reference is more. So you can write V reference by V in. So one relation you should remember. So in GATE exam, just we have to calculate here. Just we have to calculate where this number, this time, how much conversion time will be required. So here T1 is known. T1 you have, sorry, T2 we have to calculate. So T1 you can write, this is 2 raised to power n t clock, and T2, okay, T2 we don't know. So T2 you can write, sir, T2 is nothing but N2 into T clock. So if you will put this two value, you will get N1 by N2. Okay, so you can directly remember this. Sir, what will be the T2? This T2 you have to calculate, or you can say, sir, N2 you have to calculate. So number of clock required in this duration. Number of clock required. So N2 you will get here, sir, V in by V reference. V in by V reference into N1, and N1 is nothing but the 2 raised to power n. So this is the number of clock required. Now here the important thing. Suppose if N2 we are getting suppose 3.6 clock. And suppose if we are getting here, sir, N2 is equal to 3.2 clock. Then what answer you will consider? This is very, very important thing. If you are getting N2 3.6 clock, so N2 can be the integer either 3 clock or 4 clock. What you will consider? So if this is near to the next level, or you can say 4, so you can consider this 4 clock. Now if this is less than 3.5, so you can consider this 3 clock. Like this. You can consider this 3 clock. It's just I am saying. So this manual, actually we have to do this thing. Okay, so right now you don't write this thing. Okay, don't write this thing. So in GATE exam, examiner will ask you what is the conversion time. So what is the conversion time here? Conversion time is nothing but, sir, T1 plus T2. And T1 you know very well. So T1 is nothing but 2 raised to power n into T clock. So what is T1? Sir, this is 2 raised to power n into T clock. And what is T2? Sir, N2 into T clock. N2 into T clock. N2 into T clock. Okay, now the question is, sir, N2 I will consider in integer or not? Integer you have to consider. So again you can write, sir, suppose this is 3.7 and suppose this is 3.2. So what you will consider here? 3, and what you will consider here? 4. Okay, this is the binary value. Suppose, so if you are getting 4 clock, so binary value, so corresponding binary value is suppose for 3 bit 100, and corresponding this binary value is 010. So suppose, for example, if here 3 clock is required, 3.3 clock is required, sorry, 3.2 clock is required, what you will assume? Binary value. The binary value will be 100, or sorry, this is 3 means 011. This is 011. So if this is 3.3 clock you are getting, it means we will consider 011. If we are getting 3.7, so binary value I will consider 100. So because of this, your quantization error will be del by 2. So remember here, maximum quantization error can be here plus minus del by 2, not del by 2. So because you are assuming, if you are getting here 3.6 or you are getting 3.7, So you are considering next level. If you are considering 3.2, so you are considering lower level. Sometime you have to consider upper level and sometime you have to consider lower level. But in GATE exam, examiner will not ask you this thing. Examiner will only ask you, they will provide you V in, they will provide you V reference, they will provide you N. Just you remember this relation, you will get your answer. So examiner will provide you V in, V reference, number of bit, you will get N2. Thus you can put the value. So what will be the conversion time? You can write this is nothing but 2 raised to power n plus n2, and this is into t clock. Okay, now the one important thing, what n2 you have to consider, n2 will be integer, n2 will be the integer. But you have to check, sometime examiner can also be wrong here. So if for n2 integer you are not getting answer, so what n2 you are getting, just you can put that n2. Okay, that n2 you can put. Otherwise t1 and t2 you can put. T1, T2 you can find out from V in upon V reference into T1, and T1 you can put 2 raised to power n into T clock. So sometime examiner will not consider n2 integer, sometime examiner can consider n2 integer, and sometime not consider. So this is examiner choice. But practically they have to consider this n2. But n2, if you are considering integer, if you are considering n2 as integer, it means you are going to find out accurate value. But sometime examiner don't want accurate value, they want exact value, what you are getting. So that's why, so according to me right now, don't consider this integer. What you have to do, don't remember this formula. Okay, it is better you have to remember this, and first you have to calculate here T2. So sir, T2 will be V in by V reference into T1. And what is T1? So T1 is nothing but this is V in by V reference. This is T1 is nothing but 2 raised to power n into T clock. This is T2. And now what will be the complete this conversion time, T1 plus T2. Okay, so like this you can write. So this N2 should be replaced here. N2 should be replaced here. So this is V in by V reference into 2 raised to power n multiplied T clock. Clear this thing? But if examiner asks you what binary value you will get, so here suppose, okay, I will tell you what binary value you will get. I hope this thing is clear to you. Just you should remember this formula. Okay, so this basic formula you should remember. Okay, so this 2 value and n they will provide you, you can put and you will get the answer. Now sir, what is maximum conversion time? Sir, what is TC max? So TC max, here you will get 2 raised to power n into T clock, here you will get 2 raised to power n minus 1. So T1 plus T2 and T2 maximum. T1 is fixed, T2 maximum is 2 raised to power n minus 1. So here this is 2 raised to power n plus 2 raised to power n minus 1 into T clock. Sometime some teacher can also use 2 raised to power n, but this is the accurate answer. What is the maximum conversion time? So this is, you can write sir, this is TC max is equal to 2 into 2 raised to power n minus 1 into T clock. So remember this time is fixed, 2 raised to power n into T clock. This maximum time can be 2 raised to power n minus 1 into T clock. Okay, so this is a maximum conversion time here. But generally examiner are not interested in maximum conversion time. Examiner are interested in specific conversion time. Okay, now here suppose for example, if examiner will ask you, sir, what binary value you will get? So at lower person it will stop, or at upper person it will stop. This is the important point. So how you can find out? So you can see, suppose if a step size is suppose 1 volt and n is equal to 4 bit. Suppose step size is 1 volt, n is equal to 4 bit, and suppose if V in we are getting here 6.2 volt. Then sir, what will be the binary output? What will be the digital output? Or what will be the binary output? So here binary output you will get step size is 1 volt. So here 6.2 you will get this is 7 volt at the upper portion and 6 volt at the lower portion. So you will check here which is near to this, so which one is near to this? So here near one is 6 volt. Okay, don't write it will stop to 6.5 volt. That thing I have explained you for the quantizer that you study in communication system. But here if you are getting 6.2 volt, and these are the two step, valid step, one is 7, one is 6, because step size is 1. So every 1 volt you will get the step. So if one step you will get at 6 and second step you will get at 7, so this is near to 6 volts. So your digital output will be corresponding to 6 volt. And suppose we are considering here n is equal to 4 bit, this FSV is suppose 15 volt. Suppose 15 volt, it means 1111 means 15 volt. So for 6 volt you can write so 0110. This is the answer. This is the answer. How much error you are getting? So this is 6 volt and your input is 6.2. So error is 0.2. Error is 0.2. In the same situation, suppose if V in is equal to so 6.7 volt, then what will be the digital output or binary output? So sir, here digital output will be corresponding to 7 volt, and 7 volt digital will be sir 0111. So here error is 0.3 and here error is 0.2. One time positive error, one time negative error. One time positive error, one time negative error. So this how you can choose. This you can choose by this n. If you are getting here n1 or n2, sorry, if you are getting here, this is not n1, no, sorry, this is n2. If you are getting here n2, suppose 3.5 greater than 3.5, so you have to assume that equal to 4. And if you are getting less than 3.5, so you have to assume this is number of clock, here you will assume that is 3. Okay, so you don't go okay into this part. From this you should remember. I hope now this thing is clear to all of you. Where this will stop, you have to tag which step is near to that point. Okay, so here error can be plus minus del by 2. I hope this thing is clear to all of you. Only okay, only this thing you have to study for your GATE exam. So I have deal all the thing here in you can say 2.5 hours, okay, or you can say in 3 hours. So now if you are comfortable in this, okay, if you are comfortable in this, so definitely I promise you in GATE exam you can handle all the questions. Okay, so at least you can see the circuit of this. But if you don't want to see the circuit of this, you should remember this. Okay, so examiner will provide you, okay, here FSV, V reference, they can provide you step size, they can provide you number of bit, they can provide you V in value. They can ask you either question from here, they can conversion time, they can also ask you question from what is the digital output, and what they can also ask you what is the error maximum possible, sorry, what is the actual error. So actual error you can also find out from here. Clear this thing? Okay, now so next you are asking signal, when signal will start. Okay, today I will finalize. So from tomorrow maybe communication or signal I will start. Okay, so today I will finalize this. So first I have to complete this digital. So now from my side, from my side, okay, now digital is completed. Each and every topic we have dealt here. Okay, so if anybody have doubt till now, just ask me. Okay, if anybody have doubt till now, just ask me. Okay, just ask me if anybody have any doubt. Okay, or if anybody have any question regarding anything, just ask me. Just ask me. Okay, so we have here completed 5 lectures, 5 for network. So practically that is not, you can say, a only revision course. This is a one kind of crash course plus revision course, and this course will be definitely benefited which have attended. Okay, so please ask me if anybody have any kind of any query. Okay, so if anybody have any kind of any query, just ask me. Okay, and if you don't have any query, so I am going to wind up this session, and tomorrow maybe signal or communication we will start. Okay, you will get the link. You will get the link at same time will be same 5 p.m. Time will be same 5 p.m. Okay, so everyone just tell me which subject exactly you want from tomorrow. What you want, signal or communication? Okay, tell me which you want exactly, signal or communication? Which subject exactly you want, signal or communication? I'm waiting for your answer. Okay. Tell me which subject exactly you want, signal or communication? Okay. Sir, signal. After signal, tech communication. Okay, I will try. I will try for the signal. Okay. So are you comfortable in digital? Okay. So I hope now you can handle most of the question from the digital. Okay, I will try for the signal. Okay, now. So any doubt? Just ask me. Okay, so can we bind up today's session? Okay, so with next session means next subject. Tomorrow we will meet again. Okay, thank you. Take care. Bye bye and Jai Hind. Okay, take care.